One. Cool. Welcome to the RQI Circuit 2026. We are here this week in Villa Martí de la Badia in Spain at a very nice retreat workshop meeting that José Polo-Gómez has been organized for this year, this RQI Postdoc Meeting. It's been an excellent event, and now is the last day of the event, except for tomorrow, kind of. And luckily, we got some of the participants to be here and deliver some talks for the RQI circuit. This is a meeting with young junior postdocs and late-stage PhD students. So I think all of the talks will be very interesting. Looking forward to everything. Let me give it to Jose, the local organizer, and he can say a few more words and introduce the speakers.
Thank you very much, Rick. Welcome everyone to the RQI Circuit session of the RQI Postdoc Meeting 2026. As Rick said, this has been so far a very pleasant experience. I'll say a few more words at the end of the session regarding the nature of the meeting and the expected periodicity of it. But for now, let's just get going with the talks. So for the first talk of the session, we have Álvaro Álvarez-Domínguez from the Universidad Complutense de Madrid, and he's going to talk about electrifying the vacuum, entanglement, and time-dependent external fields. Please, Álvaro, the floor is yours. Can you
just put it like this?
Can you like put it in your clothes?
Okay, like that. Yeah. Okay, so thank you all. So let's talk about electrifying the vacuum. Okay, so this is a project that I did in collaboration with Luis Garay and Mercedes Martin Benito, although the very most important person here is Iker Sanz González, who is just my master student, who is defending his master thesis next week. Okay, so he's basically the boy who was in charge of everything, doing all the numerics, all the analytics and everything. Okay, so any difficult questions to him, I'm just a representative of this project. No, okay, it's a joke, of course, but he did a very good job. So now, let's start with a very brief idea of that's going to be very useful to understand what I'm going to talk about and about the electric field. But let's start then first without an electric field. Okay, so let's switch off an electric field, and then there are a lot of theorems, such as the Rees-Leiter theorem, that gives us this idea that correlations, both classical and quantum, are quite ubiquitous in QFT. Okay, in standard flat space-time. So basically, if we have region A and region B, and then we put on top of that a quantum field in the standard Minkowski flat space-time and in its quantum vacuum state, then region A and region B will have correlations, both classical and quantum, between them, okay, that relate these spatial regions. So this is the general idea that we all know have, but the question now is, what happens if we switch on an electric field? Now, the first comment is that this electric field is we treat it as a classical external agent. Okay, so we do not quantize it, and we do not, when I say external, I just say and assume that we are not going to take into consideration back reaction effects on the electric field. Okay, so basically the question is very simple: region A, region B, and exactly the same situation. We have now a charged quantum field, so that it feels the electric field, of course, in Minkowski spacetime, but with an electric field. And now we are going to set it in its quantum vacuum. You know that if we introduce an electric field, now the dynamics are not trivial, and then there's no unique notion of quantum vacuum, and some ambiguities in the choice of the quantum vacuum. I'm going to be a bit more precise with the choice of quantum vacuum that we are going to choose after. But the idea of the talk just summarizes very well with this question, the question actually. How quantum and classical correlations will distribute under the presence of the electric field. So any of you have any idea? I mean, the question is, are classical or quantum correlations will increase, decrease, or what do you expect to happen? If you have not any rough ideas, I can give some additional steps to understand why an electric field, okay? And then we can solve the equation. So why are we introducing an electric field? So there are several reasons. The first reason is because we can. Because I did my thesis on the Schrödinger effect, well, I'm introducing electric fields, no? So that's just another natural step. But there are three reasons that are quite reasonable. The first of all is that if we introduce an electric field via pulse in time, then we can understand how correlations evolve in time. And that's something that has not done before in the literature as far as we are concerned, and can be extensible to cosmology, I mean, to correlations in free millimeter worker spacetimes, cosmological expansions quite easily, right? So this is a first step that could be interesting. Second of all, well, you know that when we have a very strong electric field, then particles can be produced and extracted from the quantum vacuum. I mean, there's a threshold, which is called the Schrödinger threshold, such that if you put more electric strength than that threshold, then electromagnetic energy is kind of converted into matter, into electrons and positrons. Well, here we are going to deal with a scalar field, but basically into matter, no? And this is Schrödinger pair production, such that it marks a threshold that might be relevant also for starting correlations. I guess that once we surpass this threshold, we would expect that these correlations behave differently or something happens, right? And the third point is that introducing an electric field introduces a preferred direction. So maybe we can study anisotropies and how correlations distribute with these anisotropies, okay? So that's the general idea. So does anyone want to say something about what to expect if we introduce an electric field, or should I go on and that's it? Okay, I can go on. So I can go on with my first intuition when I started this project, okay? Because when I started this project, I had a very strong opinion. And my opinion was the following. Okay, we are going to have pair production, and these particles are going to be very entangled. There were references that already did those calculations. So basically we knew that these pairs would be very entangled. So basically my idea was very simple. I mean, particles are going to be created out of the vacuum because of this Schrödinger effect, and then these two regions will become more entangled. So quantum correlations will increase. I didn't know what would happen with classical correlations, but I had this idea that entanglement would increase between these two regions. Spoiler, no. Okay, so we are going to see that later, but that's the general idea. I had a very strong opinion on that before. Now I have completely changed my mind, but it makes sense, okay? So let's put some ingredients to create our soup. So let's electrify the quantum vacuum, right? So what we are going to do is to set a charged quantum field in quantum vacuum. And we are going to switch on an electric pulse in time, okay, like that. This is the so-called Sauter type electric pulse, which has a very precise form such that the analytics are simple. And, well, it vanishes asymptotically. But the important thing to understand, and the parameters that we are going to control here, are basically the duration of the electric pulse, which is basically given by gamma, okay? So the duration of the pulse will be gamma, well, 2 gammas if you want, and the strength will be governed by this parameter E sub 0, okay? So if we increase sufficiently this parameter, this intensity E sub 0, then at some point we expect that we are going to have Schrödinger effect. Actually, the real parameter what does matter is the relation between the intensity, the strength of the electric pulse, and the duration. Okay, so the effective duration times the electric strength of the pulse is sufficiently large, actually larger than 1/2, then we are going to have Schwinger production. Below this threshold, for weaker electric pulses, then we are not going to have a Schwinger effect. Okay? So this will be a very important threshold, as we are going to see. And now the in quantum vacuum is just from all the infinitely many different possibilities, the vacuum such that at the very beginning, when the electric field is not switched on yet, the vacuum is actually a vacuum in the sense that it's empty. Okay? So basically it's a natural vacuum such that the state is empty here, but it's going to evolve non-trivially as we switch on the electric field, obviously. Okay? And let's see how correlations evolve. So we don't start from scratch. We do know things in the case in which we switch off the electric field. I mean, in which we do not have an electric field on, right? So first of all, we know that both classical and quantum correlations will be concentrated at the interface of these regions. Why? Because of short distance dominance of correlations, right? So basically in our setup, what we are going to do is to consider regions which are disjoint, of course, but adjacent, such that we can maximize the contributions for these correlations, right? Okay, second of all, correlations are suppressed as the mass increases. Why? Well, the mass of the quantum field just fixes a correlation length. So if we decrease the mass of the quantum field, then we increase the maximum length that correlations can be inside that correlation length, right? So basically that's why we are going to take small masses. And then the last point is that correlations are stronger on lower spatial dimensions. That's why we are going to start with 1 + 1. Then later we are going to go through the last part of this talk to 3 + 1. Okay, but the idea is quite simple. If we have extra dimensions, entanglement will dilute in the other additional spatial dimensions. Okay, so that's why we are going to start in 1 + 1, because we want to watch to see this entanglement. Okay. Now, another comment that I would like to say, which approach are we going to follow? So there are many different approaches. I just select here 2 of them. One of the approaches is studying this quantum and classical correlations in Fourier space, which was basically the approach that followed the most the references that did this with the Schwinger effect or in cosmological backgrounds before, right? In Fourier space, just treating these particles and antiparticles that are going out of the quantum vacuum in Fourier space. And in that sense, these 2 particles are very strongly entangled, okay? But in Fourier space means very non-locally. And now we are going to focus on local regions, region A and region B, as I told you before. And then there are other approaches such as entanglement harvesting protocols that, as you know, use detectors, unreadable detectors or whatever. Okay? So our point, which is not our point, which is actually the point of Patricia Montiverdi and Ivana Guyot and Beatriz Bonja, which was, okay, if we had access to this field, realistically, we could only extract a finite number of degrees of freedom, because, a quantum field will have infinitely many degrees of freedom, but actually we could only extract a finite number of them, and then we just can operate locally. So we need to define very specific local regions, region A and region B, if we are going to measure that at some point in our lives, okay? And the good point of this is that if we work with a finite number of degrees of freedom, then that will be very useful for us, actually, because then we can apply all the tools that we know from quantum mechanics. to understand how correlations are taken into account. Okay? So basically, the two important rules are finite number of degrees of freedom and a local approach, okay, with well-defined regions A and B. So let's materialize this approach, and for that I need to get a little bit more technical. Let's get through this, but okay. So this is an important point. We are going to go from an infinite number of degrees of freedom characteristic of a quantum field theory to a finite number of degrees of freedom that we are going to denote with this n. Okay? So basically, how are we going to extract this finite number of degrees of freedom from the quantum field, from the infinitely many different one? Well, what we are going to do is to define this region A and region B, which need to be adjacent each other to maximize entanglement, such as I said before. And then we are going to select some smearing functions, spatial smearing functions, that define these are compactly supported functions on what? On basically the regions A and region B. Okay? So basically what we do is take this quantum field operator, which are just distribution valid operator with infinitely many degrees of freedom, and then just choose some finite number of degrees of freedom with a smearing function supported on each of them, of the regions, and then that gives us a localized well-defined operator. This chooses just 1 degree of freedom. Okay? Well, we need to do exactly the same with the conjugate momentum, and these two form 1 degree of freedom. Okay? So basically, each time that I say the word mode, what you just need to think about is just the region and how we do take into account, with a compact support function, the region. How we are extracting only what matters to us, which is the value of this distribution valid operator supported on each region. Okay? So those are modes, and obviously all the results are going to depend strongly on the modes that we are choosing. Okay? But, well, I don't want to emphasize a lot on that, but we can discuss later if you want. Nice. So any questions until here? The idea is more or less right. So okay. Now, some more technical details which are not that relevant, but we have chosen some canonical operators which satisfy canonical commutation relations. But there's a problem, because if you do this for real quantum fields, then what you find is that these are the canonical operators that will work, okay, and that you can do everything with this. The problem is that we are with a charged quantum field, and then you have a complex quantum field, and then if you do all the computations with this, these modes are actually trivially uncorrelated. So basically, we cannot do nothing with these quantum fields. We need to go to these linear combinations between the quantum fields. This is natural when you work with a charged quantum field. And the point is that now the real and imaginary part of the fields know each other. And they know, if not, they are just trivially uncorrelated. The covariance matrices are just trivial. Okay, so now this is not that important, but just if someone has interest. Okay, so now, yeah.
Can I ask you something about
the
choice of the modes for the complex field? So it's true, the phi and the pi are not going to be correlated, right? But now you're picking basically the real part of the field and then the momentum that is conjugate to that, right? Effectively, apart from a √2 factor or something like that, right? Is there any reason that you're focusing on the real part and not on the imaginary part, or are you also, because the imaginary part would also give you non-trivial commutation relations, right?
Yeah.
If you were to put a minus sign instead of the plus sign, let's put it this way.
Yeah, and you can do that. Yeah, it's just exactly.
Have you looked
and you're going to obtain exactly the same.
Okay, so you checked that?
Yeah.
Okay.
Yeah, I mean, you can. Yeah, but you are not going to. It's just the same results.
Okay, and just to make sure, if you were to pick phi and pi dagger, that would work too, right?
Yeah, actually we did that also.
Okay, good.
Yeah.
Thank you.
Okay, so the rough scheme of calculations. First of all, we are going to focus on Gaussian modes. Why? Because it's simple. It's simple, and now all the dynamics will be covered by these covariance matrices. No? So for Gaussian modes, the calculations are, well, not simple, but more or less accessible. Basically, what we need to do is to compute these covariance matrices of anti-commutators of operators between these Q's and P's that we have just defined, and then calculate the expectation values in the quantum state that we set our quantum field, the in quantum vacuum, right? So basically, we just need to compute some correlations between these Q's and P's, between these conjugate pairs of conjugate variables, canonical variables, okay? And then what we construct is a covariance matrix such that this block refers to correlations just in region A, just in region B, and the important part of this covariance matrix are these non-diagonal block matrices in which you have all the correlations between A and B encoded there, okay? So now to compute the most well-known correlation measures, what you just need to do is computing some eigenvalues, symplectic eigenvalues of this matrix or the partial transpose or whatever, okay? But the idea is that we just compute some correlation functions and then some eigenvalues of some matrices. So once we do this, then these nus and nu tildes are just those eigenvalues, and then we just can compute for Gaussian modes this von Neumann entropy, mutual information, and logarithm negativity that we are going to describe a little bit more later. But the idea that's just useful for now is that as we are going to study the time evolution of these magnitudes, we are interested in computing this at each instant of time. So this is just a bit demanding, but it can be done. Okay? So that's for the most technical part. Now let's go to results and let's see how these measures evolve in time. Okay? So let's start with the von Neumann entropy. I just remember that the von Neumann entropy just measures classical mixedness of the state. So basically doesn't know anything about quantum correlations, only about classical correlations. And well, this is not zero, okay? Sorry for the x's, I forgot to update the figure with the x's, but this is definitely not zero, okay? So basically this, of course, gives the same result. I mean, for sufficiently small times, the electric field is not switched on yet, so it's switched off, and then we get exactly the same von Neumann entropy as in Minkowski spacetime, which is not zero, okay? So we have here definitely a mixed state, because in quantum field theory that's a normal thing. We cannot have a pure state as easy, right? So independently of the values of the effective electric strength that we are putting, of course, as we are in the in quantum state, this state doesn't know anything about the electric pulse, and then we get the same result. However, as we switch on the electric field, the time evolution of the von Neumann entropy will depend, of course, on the strength of our pulse. So basically, what we see is that as we increase the electric strength, and remember, times the duration of the pulse, as we increase this product, this parameter, then we have a larger, quite an increase of the von Neumann entropy. So basically what we are seeing is that a strong electric pulses induces an increase in the classical mixedness. Remember that the electric pulse was a classical agent. Yeah.
So this is for the AB system, right?
Sorry?
So the von Neumann entropy that you're computing is for the reduced AB system, or so this behavior applies for the A?
Yeah, exactly. Yeah.
And both of them.
Yeah.
Okay.
Yeah. A, B, and both of them. Yeah. Okay. So now, a very important thing to understand here is that, look at these curves. I mean, there's quite a threshold here, and the threshold is marked by the Schrödinger pair production that I told you before. So when there's, below this Schrödinger pair production limit, there's not such an increase of the von Neumann entropy, but as we increase this parameter above the limit at which particles and antiparticles are started being created, then we have an increase in the von Neumann entropy. Okay? And another point that is relevant and is going to be seen for other correlation measures is that, look at this time, for example. At this time, I mean, remember that the time duration length of the electric pulse was 2 gammas, 3 gammas, or something like that. But even after a lot of time after the electric field is effectively switched off, the correlations, I mean, the von Neumann entropy is still increasing. So that might be a bit, I don't know, crazy at first, but then when you think that the Schrödinger effect has a characteristic, which is that it's non-Markovian, and that means that it has memory, it makes a little bit more sense, right? So even if the electric field is already off, the von Neumann entropy starts increasing, continues increasing, okay? So that's why, and the reason is basically that the Schrödinger effect has memory and knows about the past and doesn't know only about locally in time what's happening at that time. Okay, so that's a reflect of the non-Markovianity of the Schrödinger effect. And then, as a last comment about this von Neumann entropy time evolution, we see that here we have some time oscillations. These time oscillations, even when the electric field is off again. Okay. And, well, it's just a consequence, again, of the non-Markovianity, but we can understand that looking at the correlators that form the elements of the covariance matrix, okay? So if we analyze these correlators, these anticommutators, and the expectation value for late times, then what we see is that these are just a contribution when we do not have the electric field, plus 2 terms. This term is dominated by the number of produced particles of the Schrödinger effect, and this is just time independent. But this term has some time dependence, okay? And here we have the alpha and beta Bogoliubov coefficients and so on. Okay, so basically these oscillations are natural from the fact that the Schrödinger effect is happening there, and we have a non-trivial some non-trivial dynamics over there, even after the electric field is already switched off. Okay, so just a very brief comment. Anything until here or whatever? Okay. So,
I mean, if you opened it to questions, sorry to get a little bit more technical about this, right? But so you're picking many modes in each one of these 2 regions, right? Many functions G that will define, I don't know, some modes, right?
I can be more specific with that if you want.
Yeah, I would just like to know whether you're picking some sort of basis of something, or whether you're just choosing functions that have some sort of specific characteristic. But if you're going to mention this later, you can just save it for later. But
yeah, we are going to save that for later. But remember, remind me of that.
Okay, no, 100%.
Yeah, let's go more qualitatively first, and then let's go through more technical stuff. Okay, so now let's go to mutual information. Mutual information is going to be very interesting because it's going to give us the idea of because it captures both classical and quantum correlations. So this is what happens. We do exactly the same. We plot mutual information and we calculate numerically mutual information for different electric strengths. And what we see is that this mutual information starts decreasing as the electric strength, as the electric pulse is switched on. Okay? So basically, for me this was quite annoying because it went in the opposite direction of my initial results. Because we are introducing an electric field, and then that's killing, in some sense, correlations between regions A and B. Okay? What's going to happen, as we are going to see, is that as we switch on the electric field, region A and B becomes less quantumly correlated. I mean, entanglement will decrease. While later, when the electric field is actually switched off completely, then classical correlations will dominate. Okay? So basically the idea from this picture is just that at the very first moments in which we switch on the electric field, entanglement is destroyed, and then classical correlations are increased because of this introduction of the electric field. Okay? Later I'll discuss this a little bit more so that in the end we all agree that this is the natural thing to happen. Okay? And finally, let's work a little bit with the logarithm negativity. The good point about logarithm negativity is that it doesn't know anything about classical correlations, and it only knows about distillable entanglement. So it captures only quantum correlations, and this is just a clear, neat picture of what's happening here about quantum correlations. Of course, at the very beginning, when the electric field is still switched off, we have exactly the same quantum entanglement as in Minkowski spacetime without the electric field, which it's actually not zero, okay, as we talked before. And if you put a very weak electric field, then there's a decrease in this quantum entanglement, but not that much. But as you start increasing the electric strength, I remember that this green 0.5 was basically the Schwinger limit, at which above that Schwinger limit, we are having Schwinger pep production, okay? So even below, even when we do not have effectively Schwinger pep production, we have a very strong decay, strong decay of entanglement between regions A and B, okay? But when we surpass this limit, when we go through this limit, then basically the electric field destroys completely entanglement, and now the logarithm negativity is just zero, or at least distillable entanglement, because we could have bound entanglement, but definitely no distillable entanglement. Okay, so basically that's the idea. The Schwinger effect destroys entanglement, but well, I would like to be a bit more precise. It doesn't destroy entanglement. As we understand it now, it redistributes entanglement. In what sense? Well, basically our idea, and this is just the core of everything, what we thought is just the following. We have region A, we have region B, we are putting there a classical external agent, which is an electric field, and then because of that, if that electric field is sufficiently strong, it's going to create out of the quantum vacuum particles and antiparticles. These particles and antiparticles are going to be very entangled, but very entangled, if you want me to say, in Fourier space, highly non-locally in space. So basically, these particles are going to be very soon, very far away from these regions, and basically what's going to happen is that the electric field redistributes entanglement outside region A and region B. So basically, it's stealing entanglement from regions A and B, and that's why we see this decrease in the logarithm negativity. The important thing to understand is that we are studying entanglement between two local regions and not in the entire space-time. Okay? So that was our idea. Okay, yeah.
So I imagine that, like, for a given field with a given mass, if you were to increase the size of regions A and B, then, and you were looking at more of your space effectively relative to the mass, localization particles, and all these things, then I would expect basically the negativity to decrease less at the very least. Have you checked any kind of results in this direction, like of trying to basically either reduce the mass or increase the size of the regions to try to verify this idea that, well, entanglement's just redistributed, but if we were to look at larger regions of space, we would actually find it back? Or
if you, we have computed for a lot of different masses, so that, and of course, if you decrease the mass, then you increase the correlation length and you see more, you see this enhancement. And regarding increasing R, well,
it's the same thing.
Yeah, okay, it's exactly the same thing. Yeah, but what's going to happen is that it's going to focus, I mean, you have more area of the interface between these two regions, and basically the correlations are going to focus on these places, I guess.
No, I mean, it should be the same thing to basically rescale the mass or increase the size of the regions for a given mass, because basically you have two parameters here, right?
Yeah.
Which are the mass and the radius, and so, yeah, it should be equivalent. Good, thank you.
Okay, so that's the general idea, okay? So, well, yeah, the general idea, which is basically when applying a classical external electric field, classical correlations increase, quantum correlations decrease between two local regions, okay? Because pair production is just very non-local. That's the idea. So we wanted to do another calculation because Ike realized that, well, you're seeing here that this local logarithm negativity just vanishes completely. It's completely zero at a finite time. Okay, so what we did is, okay, let's compute for a sufficiently large time, I think it was 25 or something like that, and now let's compute for more discrete values of different intensities, and let's do this plot. We fix time, and now we vary this parameter, and what we find is basically this thing, which is quite interesting, right? Because it reminds us of something which is just like a phase transition or something like that, okay? Maybe it's not that easy to say that this is a phase transition because we might find all the different parameters to characterize completely this phase transition, but it's quite obvious that we have here something quite similar to a phase transition, right? So this is already known in the literature as an entanglement sudden death, and is common when you have some noisy environments. So if you are in a situation, for example, in QFT with no external agent, and then you introduce some noisy environment, then at some point, at some finite time, then you'll find that you have some entanglement death because of the noise. So basically, the electric field is acting here as a noisy agent. Okay, maybe because it's classical, maybe because, well, we already don't know exactly. I don't know if you have any idea about this, but these are the ingredients, okay? And we expect that with a classical agent such as an expanding universe, it's going to happen exactly the same, okay? So, well, one comment is that look at this threshold. This threshold is just the Stringer limit again. So after the Stringer limit, you have completely vanishing logarithm negativity. But before that, you also have some oscillations that are not computation. I mean, these are real, okay? Maybe we need a little bit more, how do you say, precision of the computer data, but these are non-vanishing, okay? So you need to wait until that threshold so that you have a completely vanishing logarithm negativity.
Have you studied that plot for different masses too? Like, is the threshold always at 0.5 regardless of the mass of the field? Or is this, have you only looked at this for a specific mass?
I cannot answer to, I mean, I know that Iker has lots of plots, but right now I don't know. I don't know what he did.
Yeah, it would just be nice to see that really, like, regardless of the mass, this threshold of the Stringer pair production will be the one regardless of the size of the regions or mass, which is the same.
I have this strong belief that this will also depend on the mass, basically, because, I mean, the usual Stringer limit depends on the mass.
Sure.
Okay, so basically, I mean, that's why we say that this first transition should depend not only on this parameter. Okay, but this is just a very important governing parameter, actually. Okay, this parameter just comes from the solutions. You see that the solution goes from being real to one term from complex, and that's why, well, more technical things that we can talk later. Okay, but yeah, there should be more parameters involved here, such as, for example, the mass of the field, definitely. For smaller masses, more production, easily. You can produce more particles, of course. Okay? Nice. So, now, a last comment that can also be very interesting because, well, we went to 1 + 1 dimensions, but we didn't say anything about 3 + 1, which is the world in which we live in, right? And why is it important, 3 + 1? Because anisotropy appears. And then now we can define a specific direction of the electric field. And we can study how correlations, quantum and classical ones, distribute depending on the direction of the electric field. And this is interesting. So this defines an angle gamma between the direction that joins the two centers of the regions and the electric field, okay? So we can ask us again the equation, how correlations will distribute. So what will happen is the following picture that we have here. So the picture is we have mutual information at a certain time t equal to 0. We only did it with mutual information. We need to do it with the other measures, but as a preliminary result. So basically what we see here is that for gamma equal to pi halves, gamma equal to pi halves, the electric field just goes orthogonally to the direction of the balls, of region A and B. And then what we see is that mutual information is maximum. And then this decreases as the electric field is just in the same direction as balls, as the regions, okay? Why does this happen? Well, it's quite understandable. Why? Because, well, mutual information is just the entropy, the von Neumann entropy of A plus B minus the joint entropy. So basically, the entropy of A and the entropy of B doesn't depend on gamma, obviously, okay? So the only thing that changes with gamma is the joint entropy. So what we are seeing is that this configuration, of course, doesn't contribute to a mixture between the correlations between A and B, because this is orthogonal, while this kind of configuration is going to increase the entropy, to decrease the entropy such that it increases the mixture between the states between regions A and B. Yeah? Okay, so that's the idea. Nice, so just the conclusions. So if we introduce an electric field in a quantum field theory in flat spacetime, we have that we see an increase in the entropy and the mutual information such that the classical correlations increase between these two local regions. But on the other way around, the distillable entanglement measured by logarithm negativity decreases, okay, between these two regions. So basically, how did we understand that? Well, for sufficiently strong electric fields, we just need to remember that we have Schwing effect, particle pair production due to this very strong electric field. Okay, so extraction from electromagnetic energy to matter. So once we have this string effect, this leads to a zero entanglement between two local regions because entanglement is diluted or very non-local. Redistribution, there's a very strong non-local redistribution via this production of pairs, which are delocalizing entanglement and not focusing on these two very specific local two regions. And finally, correlations are obviously affected by anisotropies, as we have just seen. Okay, so that's it. Thank you.
Okay, are there any questions for Álvaro? Nicetu?
Yeah, thanks for the talk. Okay, sorry. Thanks for the talk. It was very nice. I was wondering, like, if in your plots there is a relaxation back to the measures of the vacuum. So like
relaxation?
Yeah. So like you said that like the logarithmic negativity, for example, like it lowered, right? But if you keep running the simulation, like does it go back up again, or it just plateaus there?
For larger values of t, I mean, we think that these are sufficiently large values of t. I mean,
okay,
this is just t equal to 30, and actually, actually here, yeah, this is gamma. I mean, this is just going very far away. I mean, this is
all right.
We think that effectively is completely switched off the electric field. It's true that it vanishes asymptotically,
okay,
but 30 gammas is
okay,
quite far away.
And then, so if I have to understand this, what you are saying is that if in our universe, in 3+1, the Schwinger effect has happened at any point in the past, the logarithmic negativity that you would expect from two regions would be not the one of the vacuum, but rather like this lowered version, because like 10 million years ago, like the Schwinger effect happened.
I don't understand your question, sorry.
Okay.
Wait.
Can I try to
Yeah.
something to it?
Sure, yeah.
So you have to remember that this electric field here is completely global, right? So it's like what's happening here isn't like there is a region where this electric field happened and whatever, right? So it's like if you go to a box, for instance, right? And then you just switch on this electric field inside the box with Dirichlet boundary conditions, whatever. Sure, yeah. Like the consequences of this are always there. In this case, because this is global Minkowski spacetime, I mean, the electric field that happened very far away everywhere that gets there is always going to be affecting these regions. Okay. So in a sense, I wouldn't expect anything to come back to the Minkowski vacuum because there's no dissipation for far away from these regions anymore, because there's also whatever happened everywhere that's getting homogeneously to this point is going to keep being there, right? So I don't know if this helps, but this is my intuition. It's like I wouldn't expect this to come back because you have drastically changed the state of your field, and in a global way. Like.
Any comments, Álvaro?
I actually didn't understand your question before, so I think we can discuss that later. Yeah.
Thank you, Álvaro, for the talk. Could you comment a little bit more about the family of functions that you take in each region, or how many functions do you have? I think that.
Yeah. I had a slide and I decided to not write. Okay, and I cannot write. Yeah, okay. We chose different functions. Okay, the first function that we chose was just something quite similar to this with a hyperbolic tangent. Okay. I don't know. Where do I have? Hello? Okay. Yeah, something like that, representing very well this. Okay, with the hyperbolic tangent, and we had control with how you explore the limits of these regions. Okay, that's something that I haven't commented absolutely anything, and it's quite deep. But the functions that we use, the smearing functions that we used for these plots, were a family of orthonormal functions that were basically sine of 2 pi Rn. Basically. Yeah, okay. So basically, they are just, I mean, for n equal to 1 is this, for n equal to 2 is like this, n equal to 3 like that. So as you increase n, you increase their ultraviolet, I mean, they become more ultraviolet and they explore more the short distances.
Okay. So in this plot where you were showing logarithmic negativity depth, the entanglement depth, so as you increase the number of modes in each region, you have the same depth point, or
the same
so
depth point
entanglement vanishes at the same point regardless the number of modes that you have in each region?
No, that's a very good question. In Iker's master thesis will be more developed than here, definitely, but we have done a study of how many modes should we take in each regions, okay? So basically, we have done different simulations. The first simulation was, okay, take just one mode in A and n modes in B, and then do the calculations, and then take n modes and the same n modes here. And of course, if you increase with these smearing functions that I told you, the number of modes in both regions, you increase and you see more correlations. I mean, this logarithmic negativity increases. Well, increases, decreases because you see more.
Okay, and maybe one last comment or question. So here you have this decreasingly or fast decreasing logarithmic negativity, but then you were showing also that von Neumann entropy between the system A-B was increasing. So my question is, does this change happen at the same instance of time, or more or less, so that you have like some explanation due to entanglement monogamy, in the sense that so the entanglement between the degrees of freedom in the two regions A and B decreases, while the entanglement between the AB system and the rest increases. So at expenses of decreasing the entanglement between A and B.
That would make sense because of the explanation that I said about the particle per production, but we haven't looked at that, and that's interesting. Yeah, I mean, the point is that the good point is that even after switching off the electric field, you can have a sudden death of the electric field. Yeah, I don't know if that's your. We can discuss that later.
Okay.
Yeah, I don't know because I need to figure it out a bit.
Thank you.
I mean, can I just one thing to Serge's previous question? Just what about in 3+1? What are the modes that you used in 3+1? The shape of the modes for the result you showed for the mutual information?
Same one. The same, but now you need to divide by R because if not, they. Yeah.
So you use
spherical
symmetric.
Okay. Yeah, definitely. Yeah.
Thank you.
Okay. Are there any more questions for Álvaro? Okay, if not, let's thank him again.
Thank you.
That way I can use the opportunity to...
Eso no es mío.
Do we need to click something here? Or does it work?
No, I'll connect it now. Also, I know this is for the speaker, but my idea was to sit down as well. So
sit down?
Like here, because I'm gonna be.
Sit down here then. That's the only thing, because otherwise you're gonna be on camera.
Well, I was thinking that's
You want me to move
not
the
so. No, it's not so problematic. No, it's okay.
It's just a-
No, I was thinking that I didn't mind being out of camera.
No.
Okay.
Is it on?
Wait. Doesn't seem to be super well. No. No, it hasn't done it. Okay. Can you hear me properly? Okay. Let me. Okay, can you all see? No te acaba. Okay, so I'm not going to be so obnoxious as to introduce myself, but I did want to comment that I wanted to kind of mimic the style of some of the talks that we had during this meeting, so I'll use the opportunity to comment on the fact that part of the meeting was, for this meeting we had several sessions which were I mean, this is obviously for the people that were not here. We had several sessions that consisted of invited lectures that were very nice and were kindly delivered by some of the participants. And in that sense, I wanted to also give my talk as something that in the style of a sort of lecture, and to introduce this concept of macroscopic detectors that is based on ongoing work that I'm doing with in collaboration with José de Ramón Rivera and Eduardo Martín Martínez. Okay, so let me briefly, I'll sit down because I'm going to be writing. Let me briefly explain what I intend to cover. So the idea of this is that we've been talking about particle detectors for forever now, but the truth is that most experimentalists will not consider single atoms as the detectors that they actually use to measure effects in the laboratory. So the idea of this project was to come up with a model of detector that is more realistic and more amenable to the things that are usually used by experimentalists. And these things are usually macroscopic. They have many atoms, many degrees of freedom, and very often they move in random ways. So I mean, the inspiration for the model that I'm going to talk about specifically is a sort of ideal gas of unruly detectors. And in order to be able to define such a thing, we'll need to cover some things. Most of the, many of the initial, so initially I'll just, well, let me give an outline or an index. So the outline will be the following. First, I will talk about how we go from one to several detectors. This is something that many of you already know or have seen in some way or the other, but I think it's interesting to see it in the form that I will present it, also because it's for general spacetimes, and we see how something that we can call the generalized Lorentz factor comes into the picture. By the way, I will at all times in this talk about point-like detectors. So the constituents of the macroscopic detector will always be point-like. In the second part, I will well, derive the general channel up to second order that you already know, except that I will show how it can be put in a particular form. Specifically, there is we'll see how the first order is purely unitary, and then for the second order there are contributions that can be put in Lindblad form, so that they basically amount to a dissipative contribution. Then in the third part, I will actually introduce what we want to understand as macro detectors. Is everything? Can you see everything well? By the way, is everything clear? What again? It's small. It's small, but it's possible to see. Okay, I'll try to write bigger then. Thanks. So I'll give the general definition, and I'll also introduce some notions that will be useful for the final part, which is the part ultimately I'm maybe more interested in, because I want to see what is the consequence experimentally of considering this sort of detector, which is studying some responses of, well, the simplest observables of, let me call it for now, the simplest observables. And specifically, I will end up studying the response that I will study will be for the observable given by the number operator, right? which is just the sum over all the detectors. So it's the number of excited detectors. Okay, so that's my outline, and well, without further ado, let me start from the beginning. So, usually when we talk about detectors, we have a free Hamiltonian that is given by this expression in the proper reference frame of the detector, and then there is an interaction Hamiltonian that, for instance, in the case of the unruly detector, is also given. Let me explicitly write this here. So this is in the proper time of the detector, and this is equal to lambda high of tau, mu of tau, tensor phi of tau, and well, in the interaction picture. Right, as I said, I will be considering point-like detectors at all times. Also, by here, where here x of tau is the trajectory of the detector. All right, and also, just for completeness, the monopole operator in the interaction picture is given by this. So this is the unruly detector that we all know, especially for, I mean, several people here have worked with it very often. More generally, we can consider an interaction Hamiltonian that is given by some current, by the coupling of the field with some current. So in Kerr spacetimes, we will have here this factor that is so that this is defining the invariant volume form associated with the metric, and then for a specific time we can have some global function and some current J that is coupling. Sorry, let me put this here. That is coupling to the field at that point x, where this capital T of x is some global time function. Specifically, if I want to recover, I mean, this is more general than the end of the weight detector, but in particular, it allows us to recover it. So if I want that something that in the proper reference frame, so I want to pick some J of x. Let me say, I want to pick some current J of x that satisfies that, in particular, in the reference frame of the detector, and in the open set around its trajectory, where I can define its Fermi normal coordinates, it should satisfy that we recover. I mean, we should be able to recover the usual current that we get in the weight detector. So this should be high of tau, mu of tau, and this.
Sorry, Jose, could you show what is this capital T?
Yeah, this is a global time function. So it's just you can foliate your spacetime with space-like hypersurfaces, and then parameterize this foliation with some time function t.
Couldn't see what was written.
Yeah, no problem. So basically, what this is doing is just that, well, I want to define my this part, right, is my Hamiltonian density, and I'm just without the x. Well, and depending, this factor is in or not, depending on whether you want to define the density or the or the weight. And because I want to define the interaction Hamiltonian at some time t, then I just integrate over spacetime, but then I select only the foliation corresponding to the global time function being equal to t. Okay. And the thing is that, well, in order for Jx to have this form, then in particular we should be able to write it in the normal coordinates as something like this. But this means that I should be able to write in general this J of x as some delta of set of x times high of tau of x, mu of tau of x. And then I can integrate a couple of times. I can introduce one extra delta here. And then this delta, I mean, this is, well, let me just write it again. Sorry. And then I can just make a change of variables for the delta, and this corresponds exactly to doing x minus x of tau, because this is the trajectory, right, of the detector in its normal coordinates. This is the factor the change of variables introduces the metric, the determinant of the metric, and then also this minus dx d tau squared, that because the detector is following some time-like trajectory, this is just 1, and this gives us phi of tau, sorry, eta mu of eta, and then this just reduces, well, let me just change eta by tau for convenience. So far so good. It looks pretty much the same as what we would expecting. What we be expecting, except that we have this extra factor. And when we introduce this in the interaction Hamiltonian, so input this in the interaction Hamiltonian that I gave initially, which was, just as a reminder, this thing. Okay. So now if we input this expression here, now what we get is, let me just do the algebra because I think it's interesting to see how this comes out. We get the volume form here, and here we have the global time function, the delta of the global time function, and here now we have the current. And this is coupled to the field at x. But now we can move the integrals a bit around, and then let's see what comes up. The determinant of the metric cancels out, like this with this, right? And then we get here a phi of x. I know I'm doing a bit of algebra, but I think it's you'll see why. So far so good. Is everything here right? And now what happens is that this integral here, I can write it as, I can do the algebra. These are the roots. This is the sum over the roots of t of x of tau being equal to t of the deltas. Roots, I'm calling tau 0. Sum over tau 0 being the roots of the delta of tau minus tau 0 over the derivative of the global time function with respect to tau at tau 0 times phi of x of tau. Another thing is that because t is a global time function, and also because x of tau is time-like, it's a time-like trajectory, this implies that t of x of tau, one property of a global time function is that it should, like if you consider a time-like trajectory, the corresponding composition is injective. So this means in particular that there exists a unique tau which I can denote as tau of t, such that t of x of tau of t equals t. Okay. So basically this sum, all I want to say with this is that, all I'm saying is that this sum is just one single delta. And once I've done this, then I can define this gamma of t as precisely the absolute value of the derivative of the global time function with respect to tau at tau equals tau of t. Okay, and this is what I'm going to call the generalized Lorentz factor. This is not strictly a Lorentz factor because I'm not in Minkowski, but it plays the same role because what happens is that once I input everything that I've said so far, what we get is that the interaction Hamiltonian at time t is precisely given by, well, I mean, if I input this delta, I still have one extra integral over tau. Okay, so but that integral is just disappears because of the delta as well, and everything reduces to this expression. Okay. So this, as you can see, is exactly the same interaction Hamiltonian that you're used to, except that there is a generalized Lorentz factor here, which is playing exactly the same role that what would happen when we do this calculation in Minkowski, and then we have the derivative of the coordinate time over the proper time, and then this extra factor shows up. Now, why do we want to do this? Well, specifically, by the way, the same happens with the free Hamiltonian. So now the free Hamiltonian for an arbitrary time will be given by t. And the reason why we want to do this is that if we have several detectors, then in general they won't have the same proper time, so that we can. So in order to parameterize all of them, we need to consider a common time to parameterize the evolution, and then in order to consider like this common time, in general we will need these factors. So now this can be generalized. This naturally generalizes to n detectors. And now, well, basically, wherever I wrote something, I don't know. Now here we will have a sum, right, over I, and here we will have a sum over I. I'm not gonna write them, right? So now we have this allows us to define a Hamiltonian, a free Hamiltonian, an interaction Hamiltonian for a particular time, and this generalized Lorentz factor shows up. And nothing here depends on being on Minkowski or anything else. Okay, and the good thing is that here, even if this Lorentz factor kind of seems not problematic, the dependence of the trajectory of the evolution on the trajectory is completely encoded in this and this. So once so not only we have that, of course, the field is interacting with the detector wherever it is, but also the strength of the interaction is affected by what is the trajectory and like what's the relationship between the proper time and the global time function that we're using. Okay, and this will have consequences later. Okay, so that's the first part. Any questions? This is fairly standard. Okay. Okay, so for the second part, we have the general channel.
Sorry, can I ask one question about the first part? Is there any specific reason that instead of, say, just using the chain rule for changing the IDD tau to, well, exactly getting the gamma factor and then the IDD, another t or whatever, the IDDT is the evolution with respect to parameter t, just using the chain rule and getting that this is d tau dt times the proper Hamiltonian. Like, I understand that this is a more formal way of saying these things in spacetime, but apart from that, is there a good reason? Like,
well, for me, I mean, because it's a point-light detector, it might seem like an overkill, and to be honest, it is precisely because it's a point-light detector, but this is a general derivation which specifically, I mean, in this kind of derivation, we can see all the assumptions that we are making, right? So specifically, we see how this is a direct consequence of the fact that, first of all, we have a point-light detector, so that we can make the assumption about the injectivity of the global time function. This is something, for instance, that would fail if we had something that in general was extended, or even if we had some spacetime that actually did not allow for a global time function at all, right? Which is not going to be the case whenever we have a hyperbolic spacetime. So I guess it's just a cleaner derivation that allows you to see exactly what you're assuming. That would be the idea.
I think that the globalness of the time function can be relaxed under some assumptions here. But well, let's.
Well, sure. If you're operating in a local region of spacetime, then you can probably also relax that. I mean, basically, if you're operating in a local region, you can relax. You can reduce everything to the diamond that contains that local region, and then you can do things. Yeah. Yeah, so I guess as long as your spacetime is that in that case, but as long as you assume that this local diamond is also globally hyperbolic. So. But yeah, okay, yeah, thank you for the question. Any other clarification? Okay, so let me consider the general channel up to second order. So this is the calculation that is this is the usual calculation in detector, in particle detectors, where we have some initial state. I'm not going to repeat it, and just giving the setup. And in general, we can write a particular channel by on the detector by tracing out the field. Whereas we know the U in the asymptotic case, it's given by the time order exponential or blah blah blah. I mean. Okay. And then, as you know, we can expand this because this in general is the identity plus order 1 component that is proportional to lambda, and a second order plus order of lambda cube in the cases where the interaction Hamiltonian has a coupling strength lambda. And then, of course, this allows us to do exactly the same with the channels. So there will be a component that is of order lambda and a second component that is of order lambda square. I'm not going to repeat it because many of you, if not all of you, have done this several times. But the interesting part, perhaps, is that this can be reorganized in a particular way, and that will also be useful for me later for the purposes that I will show you. So, in particular, this can be written in. Let me write everything just because that way you can see the structure that it has. It will take me a little bit of time, but at least you see it. So there is a first term that is linear in lambda. Only depends on the 1-point function, and this function's gi of x that I will define later. But the idea is that in the gi of x is encoded all the dependence on the trajectory of the detector. If you see, everything else here does not depend on the trajectory of the detector. This is an operator of the detector, but it does not depend on the trajectory. This does not depend on the trajectory. So, as you'll see when I define it later, all the dependence on the trajectory of the detector is encoded in that function. And the same is going to happen with what I'm going to do now with the second order. So this is a sum over I and j, and these signs plus and minus that I'm just going to use for denoting this the ladder operators of each detector. And this is the integral over dx prime, Feynman propagator, x prime, and then there is here this hij that again they are encoding all the dependence on the trajectory of the detectors, plus hc, and finally another term in lambda square that I'm gonna do the same. Okay. Dx prime, one function. Am I running on time? Okay. I'm gonna accelerate a little bit because seeing that I'm being a bit slow.
Should ask the chair whether they give him more time.
Okay, and then this gi of x. Now you might say, well, how can you put all the dependence on of the trajectory on the detector in these functions if clearly this the field is going to interact with the detector specifically where it is? Well, just by introducing some deltas. So this is yes into the I omega s chi of s delta of x minus xi of s. Okay, and something similar can be done with the rest. I think I'm gonna skip that part because yeah, in the interest of time, I don't think it's necessary for understanding this. But the idea is that, as you see, because I introduced this delta, all the dependence on the trajectory is here. Okay, and then similar definitions can be given for Fij and Hij, and the relationship between this Hi and the Hij and Fij is exactly the same as the relationship between the Feynman propagator and the Weyman function. So actually the hij is just theta of t minus t prime, f of x prime plus theta of blah, 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 blah. So, yeah, okay. In particular, the thing is that with this expression one can massage it a little bit and get that it can be put, as I anticipated before, in the form of Limbladian channels. So this first part is the local one, and actually we'll see that this is not even Limbladian, this is just a unitary part. And then for the second order part there is a local component, a local contribution, and then there is a non-local contribution. Okay. Where, again, I'm not going to give the exact expressions because they are not very illuminating, but yeah, this part is just of the form, let me just say that this is of the form of minus I times some operator V, and then the thetas are of the form of minus this, plus some integrals that ultimately have a Limbladian form. So okay. And the idea is that precisely because this part is non-zero, then the thetas, the second order, encodes the dissipative contribution. I mean, specifically this part encodes the dissipative contribution coming from the interaction of the detectors with the field. Okay, and now given this, one can define the response of some observable A as, well, expectation value of delta of A, which is, well, the trace of E of rho minus rho A, which also can be written in the Heisenberg picture like this. Okay. I'm not going to put hats. Okay, so this is the response, and then now you see how in general I can input this and I get on one hand a linear response, a linear local response, dagger A, plus some second order local response, plus some non-local second order non-local response. Okay, and we can study this and understand where the modifications of if observable is coming from. If it's coming from interactions between different detectors, or if it's coming just from the local interaction of the detector with the field. Okay, so with all this preamble that took me longer than I thought, I'm gonna start talking about actual macro detectors now, macroscopic detectors. Are there any questions up to this point? No. Okay. Perfect. So, what is a macroscopic detector? Well, one can obviously give several definitions of this, but I think for me the idea is that a macroscopic detector is inspired by the concept of an ideal case, of something that is that has some degree of randomness, and we lack a very good control over its constituents. Specifically, I would like to establish a difference between what a macroscopic detector is and what an array of detectors is. If I have a very orderly array of 100 detectors, I would not like to consider that a macroscopic detector. That's just an array of detectors, and you can model it like that. So the general definition that I want to give is that it's an ensemble of n detectors possibly undergoing possibly stochastic trajectories. Not necessarily, but possibly stochastic. Okay? Now you can say, well, that actually does not, this definition includes arrays of detectors. Well, I will make reasonable assumptions later that will rule out that particular case. Now, in particular, notice that because these detectors follow generically stochastic trajectories, then there will, in general, there will be a probability distribution, in general joint, over the trajectories of each detector. And there might be correlations between them. They are not necessarily independent. This is not necessarily a set of independent probability distributions. Okay? Now, the interesting part about this, about the fact that we have this, is that in general, well, the fact that we have just a probability distribution, is that in general this will affect the way we transition between the Schrödinger and the Heisenberg picture. The interaction picture. How we change between one and the other. And why is this? Well, because remember that if I have an observable interaction picture, then the relationship that it has with its Schrödinger counterpart is this. But now I have to remind you that U free depends on the free Hamiltonian. So specifically this is, well, it's factorized, so it's just a product of exponentials T of t j. But this tau j of t, right, now depends on the trajectory. So this tau j of t is equal to tau j of 0 plus the integral between 0 and t of ds gamma j of s. Okay, and now this depends on the trajectory. So that means that the unitary, the U-free unitary, also depends on the trajectory. And since we're working in the interaction picture in general, whenever I have an observable that in general doesn't commute with the free evolution, then the interaction picture version of that observable in general will also depend on the trajectories of the observables. And this just makes things complicated in general, which is why I'm compelled to introduce the notion of observables of certain correlation depth. An observable of correlation depth d, that in general is, well, less or equal than n, is an observable that can be written as a sum, okay, equal 1 to d, of observables that depend exactly on the trajectories of k detectors. Okay, this depends on the trajectories, not on the detectors. I don't care if it depends on all the detectors. What I care is about the trajectories, on the trajectories of exactly k detectors. And of course, the simplest observables are those that are correlation depth 0 in the interaction picture, which are in general observables that are correlation depth 0 in the Schrödinger picture, and on top of everything, coming with the free evolution. Now, the observable that I will consider later is exactly the number operator, because that satisfies both assumptions. And now, the only thing that remains for me is to introduce these reasonable assumptions that I was talking about that distinguish this microscopic detector from any random array of detectors. And these reasonable assumptions are based on the general idea that because this is a macroscopic detector, I should not have access to distinguishing the individual constituents of the detector. So I'm going to basically impose that all my accessible observables are symmetric under swaps, under permutations of the detectors that constitute the gas, because I shouldn't have access to resolve each one of those, which is why I said before that this is kind of motivated. This is sort of a macroscopic gas of detectors, because motivated by the concept of the ideal gas, where I don't have a resolution to determine where each particle of the gas is. So what this implies is that, well, if you consider this operator that is like a permutation, swap between detectors I and J, then what I am assuming is that all accessible observables satisfy, this is self-adjoint, so that they are symmetric under these swaps. Okay, and this effectively is equivalent to a super selection rule, right? Because I'm not saying that the actual state is necessarily diagonal with respect to this or symmetric, but because the only observables that I have access to are symmetric, I will not be able to detect correlations between these subspaces. So effectively, I can assume that the state of the detectors is also symmetric under this exchange symmetry, because in any case, I should not be able to measure otherwise. And the other assumption that I can make is that all marginal distributions are also symmetric under exchange symmetry, are symmetric under swaps, under permutations. Now this doesn't mean that the distributions are independent. What I'm saying is that, for instance, if I only pick two, then the marginal distribution of having x1 and x2 is equal to the marginal distribution of having x4 and x7. This doesn't mean that there isn't a correlation between x4 and x7. It says that any two detectors that I pick, any m-size set of detectors that I pick should follow the same probability distribution. All sets of detectors of the same size are following the same stochastic process, which doesn't mean that this stochastic process should be independent ones. Although, of course, we can consider that limit. And with that, let me just advance to analyzing some of the responses. So analyzing responses, because I think this is actually the more interesting part. Responses of observables of correlation depth 0. And because I'm running out of time, I'm just gonna actually analyze n. Okay. So any questions before I move to this last part? Everything okay?
I'll save them for the end.
Okay.
Could you maybe go again through?
Yeah, I can say.
Okay, through explaining why the interaction picture and the Rodinger picture are different and.
For sure. So you agree with this expression, no? This is the expression that relates the interaction picture and the Schrodinger picture. Now, because the transition between this operator and this operator involves multiplying by this operator, and this operator is well, it's just the exponential of minus I h3, no? Tau. Sorry, the integral over the t.
Yeah.
This factorizes, and it's just, well, the product of all the free evolutions of each detector, right? But then these evolutions happen with respect to the proper time of each detector.
Okay.
Right? This is the, I mean, you can also do it with the gamma, with the exact free, like the exact free Hamiltonian that I gave you before, right? But the idea is that this is the Hamiltonian that you have to evolve with respect to which you have to evolve. Now you will get an integral over S here, right? When you compute the evolution, and this just amounts to considering tau, the expression for tau that I gave you here, which is, you see, this is the term that you have. So this is equivalent. I'm just writing here because it's a little bit simpler, but it's just the same as the integral over S of the same thing with 1 over gamma j of S. And this gamma depends on the trajectory, right? You might have a detector that is going at a certain velocity or that is at rest, and depending on whether they're following that trajectory or the other, this is different. And because that's different, then in general, because we might have a distribution. Imagine that I have a distribution that is very simple. It's just that with half probability the detector is moving with a certain velocity or with a probability is at rest. Then that probability distribution will affect what my free, like the unitary that encodes the free evolution, and therefore it will affect my definition of the I.
Yeah, I can just say that it's because you're not fixing the trajectories, and U3 depends on the trajectories. Now it's like of course, it's a...
Yeah. Yeah, I mean, if I just write everything, right, this will depend on the trajectories. This is a fixed trajectory, but then if I start taking averages over, like to compute expectations for the stochastic process, then I will have to take expectations over the trajectories, and this will affect how I have to compute HI. In particular, it tells you that in general this thing will depend on the trajectories, and yeah. And I mean, it makes sense, right? Like in general, if you think of a single detector without the stochastic processes, the way you have to transition between, like imagine that you want to work in Minkowski coordinates, right? Then the way you have to transition, but your Hamiltonians are defined in the proper time of the detector. And the way you have to transition between the interaction picture in one scenario or the other, and the other is different, right? In the case that rest, you don't have to do anything. In the other, you actually have to take into account the Lorentz factor of the detector. So it's the same, but in general, because you can consider, in general, you might have some probability distributions over the trajectories.
Okay.
And in fact, here, it may even depend, perhaps the subtlety with respect to the example I just gave is that because we have several detectors, it may even depend on correlations between them. Because now here, I will have to take like averages over the stochastic process, okay? And then in those averages, I might have, in general, I will have products between like these tau j's, like tau 1 and tau 2. And then there might be a correlation between the proper times of different detectors. So in general, this might not even just pertain to the expectation values of of each individual trajectory, but actually also involve correlations if there are any. So in general, this is a complicated. The point being, this is in general a complicated expression, right, for an arbitrary observable, and that's why I'm reducing myself to the excitation. To the number of excited detectors, because you can see that the number of excited detectors commutes with the free evolution, and therefore, well, it already doesn't depend on the trajectory in the Schrödinger picture, and because it commutes with the free evolution, it also doesn't depend on the trajectories in the interaction picture. Okay. Thank you for the question. And okay, so finally, let me see, because I don't want to be too much over time. The whole point is that because this is correlation that's 0, okay, I can take the averages already over the channel. So the channel that is going to be important for me is, well, let me denote with these two angles the taking averages over the stochastic process. Then to compute the observable, because the observable doesn't have any dependence on the trajectories, we can just compute the average of the state. Okay, and this is like the average channel. And we just need to compute this. I'm not gonna get into any details because I wanted to give you a little glimpse. Now the idea is that if we compute the response of the number operator, what we get is the following general structure. And let me assume also the exchange under symmetry. Now in that case, what we get, I want to analyze how things change with the number of particles, so the number of constituents. So that's why, let me just assume that we have exchange under symmetry. Let me consider here, assuming symmetry under exchange. The exchange of detectors. We get that the linear response is just 2n times, well, this expression, already because it's short, real part of g of x, sigma plus. And the linear, at second order, this is the part that is due to, by the way, this is the part that is due to the chi channel. Let me separate it into linear and nonlinear response. This is the part that is due to the theta channel that is linear. And this also scales with n, obviously. Okay, with some expression. No. It's just proportional to n, yes, right? That is proportional to n.
You said linear, but I mean local, right?
Yeah, local, yeah. This is due to the channel, the part of the channel that is local. And then finally we have the second order non-local response, which, let me write it like this, just so that you see, well, okay, no. It is proportional to n times n minus 1. And what I want to say is that this part, in general, does depend on the Weidmann function. Okay. Meanwhile, this part has a quadratic response, but only depends on the commutator. Which means that in general, I might have a quadratic enhancement of some effects, but these are not the effects that I'm usually interested in, because, or at least they are not the effects that depend on the state of the field in any way. So I might have an enhancement of effects that are related to the causal structure of how the field propagates, but if I want to, I don't know, have an enhancement of how I measure the Unruh effect, I won't find it in the non-local part of the second order response. And now, in particular, one can consider, let me, just to finish, I'm going to consider a couple of examples. So we can consider uncorrelated states as initial state. If I get uncorrelated states, let me consider, for instance, first example, that the initial state is just all detectors are in the ground state. Well, when all detectors are in the ground state, what I get is that the responses of like the first order and the local, sorry, and the non-local response are 0, and the second order local response is proportional to n. This is good because imagine that I want to measure the Unruh effect or anything that is related to the Weidmann function. What I'm seeing here, that I usually do it with starting the detectors in the ground state. What this means is that the fact that I have many detectors is actually not introducing any noise, because this non-local, the non-local response is still 0, and the local response, which is the one that is responsible for the effect that I'm interested in measuring, is going to be proportional to n. So indeed, if I have a very, very big macroscopic detector and it's well modeled by the ideal gas that I'm talking about, because of course in general there will be some interactions that will introduce noise, then in principle the effect is I have a linear enhancement of the response, which is good. I mean, it's something that I might be interested in. There is also the case in which I start the detectors in like ket plus state, and in this case it's kind of interesting because I observe that these two, I mean I'm not gonna say anything particular about this, just that these two are as they are in general. The linear order and the local one, they are proportional to n, and the non-local response is proportional to n squared. And you would say, well, this sounds a little bit like super radiance, no? That each detector is using like some collective modes to decay or something. But no, it isn't, because this is a paradox state. What is happening here is that we are seeing the same thing that we see in classical optics. This is just coherent emission. We have that these detectors are emitting in phase. If we had some random state mixture between plus and minus, then we would see incoherent emission. This would be proportional to n. But because we are assuming that they are all in phase, emitting in phase, then we see a quadratic enhancement in the response. But there is nothing quantum about this. This is just the same way that when you calculate the intensity in optics, this is the square of the electric field, right? And And if the electric field is in phase, then you get a quadratic response. And finally, we can consider superradiant states. Superradiant states are actually excitations of a collective mode that we can define like this. Bless you. Where the sigma plus is just. Okay. And when we compute the response for these ones, when we see basically the same things that we see in superradiance. So if we start in something like this with n equals 1, then we get that everything is proportional to n, because we know that in the extremes of the ladder of the superradiant states, the response is proportional to n. But if we pick something in the middle, then indeed we see again that, well, the local parts are linear to n, but then we get that the non-local response is indeed proportional to n squared, which is the. So we see that indeed this is a system that maybe perhaps not very surprisingly, because it's just a detector, also it's just a bunch of detectors also interacting with some field. We also observe superradiant effects. And with this I'm gonna finish. I'm already over time. The outlook of this is to be able to extend this to using more than one macroscopic detector and see if other effects that are, for instance, like entanglement harvesting and things like this, are enhanced as well, and being able to compute some of these quantities for more complicated observables that actually have non-zero correlation depth. And with that, I finish. Thank you very much. Are there any questions? We're already over time, so maybe I should not allow them. Okay, and then I guess we can finish this first session. We'll go for a coffee break now. We can be back at, let's say, 20 past, and we'll have the next session with 3 speakers. Okay, welcome back to the second session of the RQI circuit in León. For the first talk of the second session, we have Nicetu, Tibau Vidal, who's going to talk about localizing quantum information in black hole evaporation. Thank you very much, Nicetu. The floor is yours.
All right. Thank you. Thanks the organizers for this very nice meeting. Today I'll be talking about some work that I've been doing with Ricardo Falcone, Ali Akil, and Giulio Chiribella for the kind of past year. This was while I was in the University of Hong Kong. Now I have moved since January. But yeah, so basically I'll be presenting the main results from a paper that you guys can scan and watch in the archive. And then maybe if time permits, I will also present some ideas that I have about modeling black hole evaporation. And I'm very curious to have feedback from people who are within the field. As a disclaimer, what we want to say is that our field is more from the quantum information, quantum foundation side, so we are kind of approaching this topic from kind of like a different perspective than the high energy physics perspective. So if there is something that we are saying that doesn't sit right with you, just let me know, because we really want to learn, because we consider ourselves a bit new in this field. Okay, so the overview of the talk. So first I'll be presenting the paper. I think that everybody in this audience knows how to derive the Hawking radiation, but just in case I will go over it from kind of emphasizing the points that we think are relevant. We will be working in a collapsing black hole. Then the objective of our work was to really understand in terms of localization how the information was lost in a black hole in evaporation scenario. And the kind of novel approach that we bring to the table is that we will consider excited states, we will not only consider the vacuum, and we will motivate why we use excited states in order to track this information. This information flow within the black hole. And then if I have time, I will just present some ideas, let's say, about how to model the evaporation geometry. Okay, so without further ado, okay. Yeah, right, it has passed, okay. So the background is basically that we consider quantum field theory in Baidya spacetime. It's important from the foundation's perspective, to really consider what are the constituents of our system. And our system basically is a classical metric field, like G mu, and then a real scalar field, quantum scalar field. And we fix the geometry in this Badia spacetime, where the Penrose diagram is like this, where basically you have a cut and you are gluing two different geometries. So this is just a patch of Minkowski, and this is a patch of a Schwarzschild black hole of mass m. And then we need to identify the relevant regions or Cauchy regions. Also, I want to say, if there's any question at any point, feel free to just ask it. It's easier that way, I think. So then, the main regions that we have is basically the in region and the out region. The in region is just this I minus region, and the out region is the union of this I plus and this horizon H plus. Okay, and then basically what Hawking radiation is to match the vacuum that you have in the first Cauchy surface to the particle notion that you have in the out Cauchy surface. And in order to do that, what you do is you define the different modes associated to these regions, where basically we are following everybody's favorite book, Fabry and Navarro Salas. So basically, like the modes that we consider are the in modes, which are like spherical plane waves. I have to say that we are in the S approximation all the time. Like we consider like only spherical shells. Like we don't consider any angular momentum or nothing like that. We are just keeping it very simple. So it's kind of like we are not technically reducing to 1 + 1, but like for all practical purposes, like we will be working on the diagram, and we don't consider like spherical deviations or spherical harmonics or nothing like that. So at I minus the modes are these ones, and then like in these different regions, like you define the natural normal modes given by the wave equation that takes into account the curvature of Schwarzschild, and you see that you have these kind of nasty looking things. And then what it is done generally is like then you calculate the Bogoliubov transformation between these different sets of modes that give rise to different Fock spaces, and you want to match them. And the way you match them is like using these Bogoliubov coefficients, and also, I don't know what happened. I'm sorry, guys. It's just I don't see the arrows in my computer, so now, sorry. Oops. I'm very sorry. So you not only connect the different creation and annihilation operators, you also connect the two vacuums. So like just for notation's sake, like it's important for the talk that you understand that the B's are the annihilation operators associated to the modes that are localized within the region that will fall into the interior of the black hole. So like if you remember, so like basically from VH to the right, the C's correspond to the modes that will evolve towards the exterior of the black hole, and the A's are the natural plane wave modes that are completely delocalized within I minus. Sorry that I have some issues. Okay. All right. And then what we know and what is important is that the vacuum, it's an entangled state with respect to the outside vacuum, and that leads to the Hawking evaporation and the black hole information problem, let's say, loss problem. Okay, so the problem basically is that since we have that entangled state, since we don't have access, or an observer on the exterior of the black hole doesn't have access to the interior degrees of freedom of the black hole, they need to trace them out. Once you trace out this entangled state, like you obtain this mixed state. It's a mixed state that happens to be thermal with some characteristic Hawking temperature. And then like there's this argument of that since the field has some temperature, as if the black hole was radiating, then the mass of the black hole must decrease. And then the argument goes that the reduced black hole will continue to evaporate, and up to some point that we don't know like what will happen with quantum gravity effects, but only if you just consider the semi-classical model, then the black hole will completely evaporate, just leaving behind this thermal radiation. This is kind of like one of the black hole information problems. And basically, like we want to understand this problem better, of like this, how it's happening, this pure to mixed transition, of what are the assumptions in this argument, and whether we can understand or model better some of these assumptions. There is another related black hole information problem, which is that there have been some calculations, and what seems to be the claim is that the details of the collapse are lost in the radiation. So it doesn't matter how the black hole collapses, all the information about the collapse does not get an imprint on the black hole, on the Hawking radiation and the radiation that will escape the black hole interior. Okay, and this second problem is one that I think in our paper we have been able to resolve quite nicely. Meanwhile, the first one, it's still work in progress, and like our contributions, I don't think they say much about this one. Okay, is there any question? I guess that's a no. All right. So in order to kind of track the information that we have, we want to have some notion of localization of that information. And for that, like, we just use a very crude idea from algebraic quantum field theory, which basically is to identify the algebras associated to different regions of space-time by just given the field and the conjugate momentum algebra generated of that region. So this is what I was saying before. Usually you define the interior of the black hole states as the states that correspond to the modes being localized here, and the exterior of the black hole, like the modes, the natural modes, being localized here. But what we have been able, and this generates like there's a natural tensor product decomposition between like this region and this region. But what one can do is like that if one propagates back these modes, like there is an equality identification that the algebra, at the level of the algebra, so the interior of the black hole algebra, corresponds exactly when we propagate back at I minus as the algebra of the operators that have support over this region of these VH, which is kind of the point that generates the event horizon. So let's say any localized operator here can be mapped to a localized operator in the exterior of the black hole, and any localized operator here can be identified as an operator that acts only in the interior of the black hole. Okay. Any questions? Okay, that's fine. So once we have this kind of identification of the different regions being like concrete spatial regions in I minus, like then we can apply, like, again, we come from quantum information. What we want to now know is to track the flow of information. But from quantum information, it's very understood that information is something that you need to encode, right? And that if all you consider is like one single state, so that information is a counterfactual, it's related to counterfactual properties. Like you need some sort of agency, some sort of transformations that you have to be able to do in your system. Otherwise, like there's just no information. Like you just have one state. There's no bit, there's no qubit, there's nothing. You just have one state. There's no information. So in order to consider encoded information and like to track the different, to track the information flow, what we consider is we will excite our vacuum state with local excitations, and then see how these local excitations propagate through space-time and whether like they escape to the exterior of the black hole or they remain in the interior of the black hole. Okay. So what we want to check is like whether if all initial pure states produce the same radiation state, because then it would mean that all the quantum information is completely lost, right? Like it just means that it doesn't matter what you do to your initial state, you will get your Hawking radiation anyway. You will get your you'll get your Hawking radiation anyway. So like the black hole is eating all that quantum information. But if not, there is some information flow and there is some partial eating of the information, and we want to like exactly characterize what is this this information loss, let's say. The way we calculate this is basically like we will excite our state in I minus, then we apply the Bogoliubov transformation, and then we take the partial trace over the interior degrees of freedom, and that will give us the exterior density matrix, and then we will see if the exterior density matrix is the same or not as the Hawking. I don't know what's going on. I'm sorry that I don't know what happened. Okay. How am I doing time-wise, guys?
You still have basically half an hour.
Okay, that's fine. That's good to know. All right. So in order to characterize this loss of information of which transformations you can do to your state and whether that will give them an imprint on the exterior of the black hole reduced density matrix or not, we apply this very widely known theorem, which is the Schrödinger HJW theorem, which basically says that if you start from a pure state in a bipartite system, and so you start from two different pure states in a bipartite system, you take the partial trace over the interior of the black hole, and the marginals on the exterior of the black hole coincide. That happens if and only if the pure states in the first place were connected via a local unitary operation on the interior of the black hole. So what is important here is that first it needs to be local in the interior of the black hole, and this intuitively makes a lot of sense because like if I'm doing some transformation on something that I know that will fly already to the exterior of the black hole, so if I do a local unitary on the exterior of the black hole, it makes sense that that will give an imprint on the exterior of the black hole. It's kind of like I'm just sending information there. That is kind of like, I think it just makes sense. But so it makes sense that it needs to be kind of what is lost needs to be localized within the interior of the black hole, but what is important is that it needs to be unitary. So if you consider some excitation, so if you consider two states that are related by some excitation on the or some operator in the interior of the black hole, but that operator is not unitary, you have the possibility of modifying the radiation state. Okay. And this is what we have kind of checked to also understand. So this is kind of our result in terms of localizing the information that is being eaten by the black hole. Now, another thing that we were kind of surprised when we were like looking at Fabry and Navarro-Salas and like other literature is that how one does model this shell of mass that creates the black hole in the first place. Because like we come from quantum information, so we are used that everything is quantum, right? And especially for the second black hole information problem, which is that the details of the collapse do not have an imprint on the radiation, for us it was kind of natural to say, well, the radiation is of a quantum system, right? So the details of the collapse, the kind of information that I'm willing to see if it's lost or not, should be quantum also, right? So what we do is we model the mass shell that collapses and forms the black hole at V0 as a quantum excitation of the field that we will consider the Hawking radiation on. And this is just because, as I said in the very beginning, like our system just has the metric and the quantum field, right? So it doesn't make sense to think now of a third kind of classical system that has this, that acts as a source of the metric, And also it makes sense for us because like we believe that ultimately all the matter that you have in the universe is quantum. Like I don't know any kind of classical model of matter, to be honest. So it just makes sense for us like to model the collapsing matter source as some excitation of some quantum field, okay? And then that justifies us to just consider excited states that are not locally unitarily connected to the vacuum. We just use very simple states like one particle and two particle states. And then we compare the expectation value of the number operator of exterior of a black hole particles to the vacuum expectation value, which is given by this thermal profile. Okay, and I really want to make the point that this is not, we are justified in doing this because this is not a vacuum solution. A vacuum solution, so if you look at the Einstein field equations, right, you really need that your T mu nu has some delta at V0. Like otherwise the equations do not match. So like in our view, it doesn't make sense to just put the vacuum where the regularized stress energy tensor at I minus is completely zero. You don't have this delta. So already on the get-go on your equations, you have like a huge discrepancy between the left side of the Einstein equation, let's say, and the right side of the Einstein equation. So we really think that the correct states to model black hole evaporation like should have some sort of nice profile of some mass m being more or less localized in V0. Okay, is there any question?
Yes.
Okay.
So just to understand clearly what's happening here. So first, you mentioned how to basically map these final degrees of freedom like asymptotically into initial degrees of freedom at square minus and what goes into the black hole or not, which is super cool. And then the other thing that you're doing now is that you're considering a state for your field, like an initial state, that will match the stress energy momentum tensor of a dA spacetime. So it's basically a collapsing like state that has total energy m, such that it would form it would satisfy the semi-classical Einstein equations with this back reaction up to some extent, like
kind of. We do it a bit crudely, you will see, but this is what we're doing.
Okay, cool. Thank you.
So sorry, the logic for the counterfactual argument that you said, right, is to analyze whether everything that's happening in the black hole happens unitarily, because I mean to see whether you get different. To use that argument, the HJW theorem, to argue that if things happen non-unitarily, then you should observe. You should potentially observe different Rhodesian states, but the HJW theorem heavily relies on the joint state being pure. So if something happens non-unitarily in the black hole, then I mean, again, I'm just following the argument, not. Then in principle it could be the case that after the interaction with the black hole, then the final state is mixed, and then the argument doesn't hold anymore.
That makes sense. No, the HJW, what is important is that the initial state is pure. So
both are pure. Otherwise, the if and only if doesn't hold. Like bar phi and phi. I mean, that statement is clearly not true if you allow mixed states.
That's I completely agree. The assumption that we make is like that the state at I minus is pure. That is an assumption that we do.
But then, at I minus.
That's true. I think that's my intuition. It's a good point. Like I have not checked, but I think that because of the properties of the Bogoliubov transformation that matches I minus to I plus, it will send pure to the full Cauchy surface. Like the state, so for example, sorry,
Yeah.
here, this is pure, this is also pure.
Yeah, I understand, but then
I agree that maybe we should just check, like to be super sure. But I agree with you that we are assuming that Boolean transformation matches pure to pure.
No, that I agree with. That I don't have any problem with that. But then I don't understand the argument, because if are you saying that all the interaction that's happening in the space-time, you can just reduce it to the Boolean transformation? Then you're imposing by fiat that it's going to be unitary. No? Like, isn't that circular to some extent? Maybe I'm not understanding the argument properly.
No. Okay, I understand. We are imposing by fiat that it's unitary.
Okay.
That is 100% true. What we are saying is that, so the HJW theorem, what it says is that if you are already in sigma out, right? And it's like, imagine you have one state in sigma out, like two different pure states in sigma out, right? But imagine that then you trace the interior of the black hole of these sigma out pure states.
Yeah.
And the marginals in the exterior of the black hole are the same. What does this tell you about the overall structure of the full state, of the full pure state on the whole sigma out? And what the theorem tells you is that the two states are necessarily connected by a local unitary in the interior of the black hole.
Okay, so what you're testing here is the locality of the...
Yes.
Okay. So you're not testing the unitarity of the interaction.
No.
You're testing... okay, sorry. I missed your point.
It's all right. Thanks for the question. It's good to clarify this thing. All right.
Can you catch it?
Well, okay. So you mentioned in passing that the quantum state you'll assign to the incoming modes will be a 1 or 2 particle state.
Yeah,
then you'll
this is what we have modeled, yeah.
Yeah, like I'm just thinking that you're then going to use the semi-classical solution of Vajja spacetime to compute the Bogoliubov transformation, right?
Yeah.
But if the fluctuations of your stress energy tensor on the quantum state that you use as the input are not under control, then does the semi-classical approximation still hold? Like if you replace the one particle state with a coherent state, I would be less worried. But how important is the assumption?
We don't do coherent states just because like coherent states are unitarily connected to the vacuum, right? So then, like if you have a coherent state, you will see nothing. Like the Hawking radiation will be the same. Does that make sense?
Yes, but then
I understand that, like for us, like our perspective is kind of like the semi-classical approximation already breaks down if you are choosing the vacuum, because like at V0, one side tells you there's a delta function, the other side tells you it's 0, right? So we are not very worried, or maybe like this is a criticism of our work, that we are not super careful about whether these things are controlled or not. Like this would be something like more for the future. I don't know if I'm answering your question.
No, I understand. I just want to make sure that I understand what are the implicit assumptions here.
Sure.
Because the original problem you started with was a statement in the semi-classical evolution.
Yeah.
So if you had a classical energy momentum tensor and quantum field fluctuations on top of that, the state of the Hawking radiation would be indistinguishable, assuming that the input state was such that the semi-classical Einstein equation applied. And it sounded to me that what you're doing might be breaking that. So
I understand. It's completely semi-classical. Like we're not putting fluctuations on the metric, I have to say.
Yeah, but I mean, I wouldn't trust the semi-classical equations of motion if the state of the quantum field is not, the fluctuations of the energy momentum tensor are not under control. And the example I have of that is
I understand. Like we have not completely checked the fluctuations of the stress energy tensor, and like I think it's a valid point. Yeah.
But I guess it's like what you could do, just to both have a state that is not unitarily connected to the vacuum and make Bruno a little bit happier, and myself too. It's just you could perhaps consider a superposition of a coherent state and a one particle excitation or something like this, such that the one particle component is way smaller, and then you have some control over this. But it's I mean, we can probably discuss about this later. But it's and about this idea that like the fluctuations of the mu have to be under control. I mean, it's like are they for the vacuum? So it's just I would just say that we don't really understand when semi-classical gravity works. We just hand wave a little bit and we argue some things, right? But it's there's no well-defined limit for when semi-classical gravity should work. We just know that it should in some limit because it kind of does, and matter is fundamentally quantum. So yeah.
Okay, so if there's no more questions, I can just go to the crude modeling we did, which basically it's the modeling. We just considered like one particle and two particle states with respect to two different kind of modeling schemes, let's say. The first one is just very crude, which was we are people that usually work with qubits, so we want things simple, no integrals, no nothing. So what we consider is that the excitations that model the collapsing shell are just given by the annihilation operator, the natural annihilation operators on the interior of the black hole, which it's a bit convenient for the math because like you will see the results are very clean, but in terms of actually modeling something at V0, it's not like you see this is the spatial profile of the mode, so it's not fantastic. Okay, let's say in this regard, but it gives us like a lot of clarity and like seeing like that the effect is really there when you have some operator in the interior of the black hole that is not unitary modifying your initial state, right? And then the second thing is we try to refine our findings a bit more, and we used a Gaussian profile picked around V0 with some oscillations that make it such that when you do the Fourier transform into momentum space, it's heavily peaked also around M. So like this is kind of like a Gaussian wave packet, let's say, centered around V0 and with total, or at least with expected mass M, okay? So it's given by this profile, and basically the scheme that we do is we compare one particle states of total mass M with two particle states of mass M half, okay? So the idea is that effectively this will be modeling the same mass shell, so these are like the details of the collapse, let's say, and then what we compute is the expected number of exterior of the black hole particles, and what we see is that there's deviations, that there are different deviations from the vacuum, so that clearly this is not only different to the vacuum, like this is different to this. So the exterior of the black hole expected radiation is different from the single particle case and the two particle case, okay? So we can kind of say that the black hole has some quantum hair that tells you about the details of the collapse, okay? So kind of solving one of the black hole information problems, let's say, all right? And these are like clearly different, and like you could ideally with many rounds, whatever, you could distinguish the two states. And then we did the same, which I'm proud of because I could prove I could perform integrals after 6 years of not doing so. So we considered like this single particle black hole of a single Gaussian shell of mass M, and then we computed the expected number of particles. It involves these nasty integrals of like all this crap with the Bogoliubov transformation, which it also looks nasty because it involves gamma functions and all this kind of stuff. I'm sorry. Okay, and we compared again like the single particle state with the two particle state, and you can see that the differences are just on these integrals, and when we have m-half, you have a 2 factor there, but you need to change this wave function, all right? And the cool stuff is that these are heavily oscillating integrals, so to do them numerically, it was a nightmare, so it was easier to do them analytically, okay? So we could perform the analytical calculation, which is quite cool, like something that like you have this nasty integral and you have the very well-known hypergeometric function u. Okay, so yeah, this is the nasty result. I'm sorry, it's not very pretty. But since we did the analytical calculation, like then we could do a nice plot without worrying about numerical integration and this kind of stuff. And this plot shows you the expected number of particles in the exterior of the black hole for a given k, where k goes in the x-axis and the y-axis is the expected number of particles. And there's 3 lines here. The blue one is the vacuum, okay? The green one is the single particle state, and the orange one is the, how it's called, the 2 particle state of mass m-half. And you can see that like they are clearly different in this regime, at least, so that there is a minimal imprint on the, at least a minimal imprint on the Hawking radiation from different particle excited states. Okay. All right. So this is the conclusions, kind of like of the paper. So the first part of the talk, which is basically is that the quantum matter of the collapsing black hole will partially be radiated away. Okay, the details of the collapse can be have an imprint on the radiation, and finally that the information encoded in local unitaries in the int region is still lost. Okay, so like we had to do this non-unitary excitation in order to imprint some of the quantum information, but if the modification was unitary, local unitary in the interior of the black hole region, that is still lost because that completely falls into the black hole and keeps the shape of the entangled state. Therefore, when you take the partial trace over the interior of the black hole, the Hawking radiation state that you have, it's the same. Okay. So now, how much time I have left?
5 minutes.
5 minutes. 5? That's okay. All right. That's cool. I just want to say these are some ideas that I've been thinking. So there might be already done by other people, etc. So this is also like personal work, has nothing to do with the serious people that I collaborated on the other paper. Okay, this is at my own risk, let's say, which is one of the things I'm interested in is like, now that we know how to treat like excited states, one thing that was very dissatisfactory for me in the black hole information story was like this hand-wavy thing of saying, oh, the black hole will reduce and then it will continue to evaporate. And I really wanted to put that into kind of like a Penrose diagram idea, and I've never seen that, and that is kind of like the motivation for some of the ideas that I would like to explore here, which basically is that, so we have this collapsing shell, right? And so in this Badia, at least model, you just don't have any back reaction, you don't have any evaporation going on. Like the story here basically is you start with a vacuum state. This is Minkowski. This is Minkowski. This is how it's called. This is Schwarzschild. If you start with a vacuum, or if you start with some excited state that models actually the collapsing mass m, whatever, it will evolve. Here you will have some the field will be excited, so like you will have some information, the field will have some excitations here, but that's it. That's the end of the story. There's no, the black hole continues to evaporate, or no, nothing. That is something kind of done like a bit hand-wavy, a posteriori, and like saying, oh, because there is like conservation of energy, then the black hole needs to shrink and this kind of stuff, but it's not modeled at the level, at least that I have seen, at the level of Penrose diagrams in a way that I could understand, let's say, but maybe it's my fault, right? So the idea basically here is to consider more gluings of spacetime, because intuitively the idea that we have, right, is that here we have Minkowski, here we have a mass shell of mass m that makes this part of the this part of the spacetime Schwarzschild of mass m, right? But then the intuitive reasoning that we have is that Hawking pairs will be created and then they will be emitted away, radially outgoing, right? And that will make the black hole shrink, okay? So the idea basically is like to model these emissions of radially outgoing with certain mass m, or like effective mass m. And then you should glue into this patch also a Schwarzschild geometry of mass m minus, like big M minus small m, where the small m has been lost here, okay? And one of the cool things is that there is, I have some justification on why you can consider these emissions towards the right, but I don't think I have time for that. One of the cool things about this is that then you can use, or at least my idea is to use this machinery that we have developed of considering the transitions of excited states to kind of like, you start with the vacuum or you start with mass shell m, and until here you have, so here it's kind of like the previous horizon, like you put it a bit before the horizon of mass m, let's say. So you calculate the transition from here to here. You can do that analytically. Instead of gamma functions in the Bogoliubov transformation, you have incomplete gamma functions in the Bogoliubov transformations, which is a bit of a nightmare, but it's okay. So you can calculate the transition from state from here to this kind of Cauchy surface, all right? Then you can check how much energy is going away, so you can kind of fix a bit the position of this emission and the effective mass of this emission. But then you still need to remember that there is some flux going in, and then you can calculate in the Schwarzschild of the reduced Schwarzschild m minus m, how does this state may arise as some state where you propagate back, and then you can propagate forward using the known Bogoliubov transformations of that involve the gamma functions between this surface and this surface. I don't know if that was very clear. I said it a bit rushing, but feel free to ask questions. This is kind of like the idea. Ideally, then you would do this sequentially, so like one emission, two emissions, whatever, until it gets to a point where you basically end up emitting or radiating away the kind of like little black hole. This is still very semi-classical. It's not a quantum theory of gravity, blah, 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 blah. But then when you glue like this patch of Minkowski, it's very clear that you will have pure-to-pure evolution. And then like there's all these questions of how does the page curve will look here, whether like thermality will be preserved or like the correlations of the incoming fluxes like then will be correlated in this Cauchy surface or not. But yeah, this is something I would like to think. I don't know if it makes sense. I don't know if it's done. I don't know if it's interesting to you, but I wanted to speak to you about it to see what you guys think. And yeah, That's it. Just a reminder that, yeah, if you create a black hole of different colors, you will be able to detect these colors after some time in the evaporation. But yeah, thank you very much. Questions? Comments?
Are there any questions?
Critiques?
I just wanted to check the story. So you're saying that there is a problem that the Hawking radiation doesn't know about the collapse, about the particular process of the collapse.
Yeah.
So then what you decide is, okay, I'm gonna consider a collapse model, and then I'm gonna try to model how matter, excited states fall in, and if that affects the radiation, and you see that there is a difference when you consider local excitations, right?
Yeah.
And then you see that there is a difference.
Yeah.
I'm a little bit worried about the unitary inequivalence of writing down local excitations with respect to the initial vacuum, because that doesn't split well into. So actually a local excitation.
Yeah.
Doesn't belong to the initial Hilbert space of the vacuum in Minkowski, I would say. Those are excitations that in the asymptotic past have infinite energy. I was wondering if one could consider other types of preparations that actually are more friendly to the.
Sure, maybe, yeah. The thing is, we come from quantum foundations, so single particle, two particle states seemed natural and normal for us. But yeah, if you guys have some ideas of the interesting thing is just it does not need to be a unitary. So if you yeah, as long as it's superposition of coherent states or something like that, then we are happy, because I don't think you can implement a superposition of maybe yes, I don't know, to be honest. But yeah, that is the only condition that we have.
Okay.
But yeah, but I don't know how this well-behavedness is.
And for superpositions of coherent states should be alright.
Okay. Yeah, I need to think if that is still unitary, but yeah,
that was not the.
Yeah.
Any more questions? Okay, then let's thank Nicetu again.
Thank you.
Your next speaker is Sebastian Murk. Actually, I realized that I thought we were your surname was in English, but I guess it's Murk.
Yeah.
So Sebastian Murk.
Out of the way. So this is the limit of the chair. Okay, I'm actually going to use the chair because I know that I'm going to pace otherwise, so and block stuff. Okay. So.
Okay.
If I use this laser, the people online can see that too if I point here, right?
That's a good question. It will depend on the lighting of the after we put on the slides.
Okay.
Because the like right now everything is very dark, so of course they would be able to see now. But after it becomes I don't know, is your presentation dark background or light background?
It's black on white, at least for the most part.
Yes, the chain.
I think it's just because it's twice, right? We can just go.
Just try to put it once. There's no reason to have it twice like that.
Yeah. Allow, and now entire screen. Oh no! Now
Nice.
it messed up some dimensions. But if I go to presenter view, then hopefully.
Is it okay?
Yeah, I think this works, right? And I can go. Yeah. Okay.
Okay. Perfect. Okay, so then, as I was saying, The second speaker of the session is Sebastian Murk, who's now in Charles University. He's going to talk about classical quantum gravity as quantum gravity in disguise. Thank you very much, Sebastian. The floor is yours.
Yeah, thank you very much for the introduction and for having me here. Can everyone hear me, or is it too loud, too quiet? Good? Okay, great. Yeah, so the title of my talk today is actually coinciding with the title of the paper on which the talk is based. And so this is a collaboration with Masahiro Hotta from Tohoku University in Sendai and Daniel Turner at Macquarie University in Sydney, who may be familiar to some of you. And I've structured the talk to make the title meaningful rather than just provocative. So the main question that we try to address in the paper is, can completely positive classical quantum theories be fundamental? And this will also be the overarching theme that sort of reappears throughout the talk. And I'll start off by providing some context and some background for the classical quantum formalism. So we'll see what actually is a classical quantum state. I'll talk a little bit about the physical significance of completely positive dynamics. And then our main result, which concerns embedding these classical quantum theories into theories that are actually fully quantum. And if time permits, I will show a toy model as a concrete example to illustrate the implications of our result. Now, zooming out a bit, the bigger context of this line of research is gravity quantized, or do we need to quantize gravity? And one of the possible alternatives to quantizing gravity that have recently gained attention are these classical quantum hybrid theories. So these are theories where gravity remains classical, but it can interact consistently with quantum matter. And you may have seen some of these recent papers by Jonathan Oppenheim and collaborators. So these are central examples of proposals for classical quantum hybrid theories. But there are, of course, many other people working on this as well. And I will not have time to show all of their papers, so I will just give two more illustrative examples, namely this paper by Galli, Giacomini, and Selby, which shows that if gravity is indeed classical and interacts with quantum matter consistently, then this interaction must be fundamentally irreversible. This is also something that will reappear in my talk today. And since we're all gathered here under the auspices of relativistic quantum information, I thought it would be appropriate to mention that there are actually now proposals for quantum information theoretic approaches that are aimed at investigating whether gravity-mediated entanglement can actually serve as a witness for the non-classicality of the gravitational field. So the exciting part, at least to me, is that this is really now entering a phase where it's no longer merely philosophical, but we actually will be or should be able to really test and distinguish different models based on their predictions in upcoming experiments. All right, so what do we actually want from our theory of classical quantum gravity? And of course, we want all of the usual stuff. We want our probabilities to be conserved. We want to be consistent with the second law of thermodynamics, and so on. But most importantly, we want something that allows us to describe the mutual back reaction between a classical gravitational field and quantum matter in a consistent way. And one of those two directions will already be familiar. Namely, we know, okay, classical gravity affects how quantum matter behaves. And we already know how to deal with this, at least to some extent, namely when we do semi-classical gravity, or more generally when we do quantum field theory in curved spacetimes. The trickier part is how to deal with this back reaction of quantum matter on the geometry when the geometry is supposed to be classical. And the reason that this is trickier is that if the gravitational field is supposed to remain classical, then this back reaction cannot just be an ordinary deterministic Hamiltonian coupling. So if you want classical quantum gravity with completely positive dynamics, then you have to have things like noise and stochasticity and decoherence and diffusion. Okay, before I get into the more technical part, I should also mention there are different attitudes towards these hybrid classical quantum theories. So there are people who use those theories as an approximation, and there are people that are more in Jonathan Oppenheim's camp where this is really a proposal for a fundamental theory of gravity. And of course, those two things are very different. So if you want to use this just as an approximation, you might have a situation where actually both systems are in fact quantum, but it might be computationally cheaper to treat one of them as classical if it's very weakly quantum or for other reasons. And I'm just going to skip through this a bit. So in this situation, it's actually not a deep problem if this approximation breaks down at some point. It just sets the timescale for which this approximation is valid. And like I said, the classical sector may be effective. So you might actually have two systems that are quantum. One's very weakly quantum. So you can model it more cheaply computationally if you model it as classical. And typically people use this for the purposes of computation. Now, the other camp is really different, where this hybrid theory is supposed to be a fundamental theory of gravity. So here, if this breaks down at any point, this is not just a problem that your approximation breaks down because it's not an approximation, but this would really be a fundamental issue of consistency here. And along with that, that it's used as an ontology, the classical sector is fundamental. So this is not an effective description, but there is really something classical in the real world about the gravitational field. Right, so let's briefly talk about how to describe a classical quantum state. So this will be a density operator that you're familiar with from quantum mechanics and quantum field theory, but it will depend not just on time, but also on classical phase-space variables z. So typically, this would be your positions and your momenta. And we can recover the states of the subsystem. So if you want to look only at the classical subsystem, then you can simply trace out the quantum system, and then you will get some distribution set of t. Now, on the other hand, if you integrate over the classical variables, then you will end up with a density matrix that describes the state of the quantum subsystem. And any reasonable theory should be normalized such that if I integrate over the classical variables after I trace out the quantum degrees of freedom, then I should get 1. Now, I've also mentioned complete positivity already. So the question is, why is this an important component? And many of the earlier schemes for classical quantum hybrid dynamics and theories of gravity were actually reversible linear schemes. And these are very attractive because they just behave like Hamiltonian systems with unitary evolution and so on. But it turns out that generally, you will run into consistency problems with these theories. So this is also where the paper by Selby and Giacomini and Galli comes in. And these inconsistencies arise precisely because when you couple quantum back reaction to a sector that is classical or supposed to be classical, then this is incompatible with an evolution that's reversible and linear. Yeah.
I always had, unfortunately I haven't checked those papers. So I always had trouble understanding exactly what they mean by, what is the logical inconsistency? Or is it just inconsistent because, I mean, I cannot think in principle, I think of semi-classical approximations, but it's difficult for me to imagine how I would like couple the quantum system and the classical system. So when they say that all these hybrid couplings are intrinsically inconsistent, is there like a logical inconsistency that you can reach by assuming that they are coupled somehow? Or what is that inconsistency?
Yes, I believe so. Okay, so what I'll show in the talk is that if you have something that's based on completely positive dynamics, then you have to have some sort of decoherence and diffusion. But that's actually what makes it irreversible. But this is what, it's like I think the best way I can explain it is if you have something that's completely positive, you can model this back reaction consistently, but it's precisely because you need those decoherence and diffusion terms. I think it'll become clearer later in the talk. There's actually an inequality that sort of balances this. If it doesn't become clear, we can chat more later.
Will you explain what do you mean by consistent or inconsistent? Because this is really what I have trouble.
Yeah, the problem is if you have random stuff, then generally it's hard to make this a linear theory, right? If you have random stochastic elements.
Yeah, but that's the leap for me. That I understand it is hard. But there is a gap between hard and inconsistent. You know.
No, I just want to clarify. Maybe I have the right intuition about this. If you want the one part of the system to stay classical, then you cannot make it reversible.
I understand that part.
Yeah.
I don't understand the thing about things being consistent. Oh, it's because
because it's not consistent to say that one part of the system stays classical, because if it was reversible, This is a question mark. If
Yeah,
it
I
was
mean, the
it
simplest
was
way of seeing
a
is
part
this-
of the classical thing would become quantum after, right, or something like that.
Yeah. You can also think of using Stein-Spring dilation theorem, and you embed it into a larger system, like it's coupled with some environment, and then you will see that you cannot make this reversible, unless you have this diffusion and decoherence and these stochastic elements.
I guess I have to check it's just that I would like to see exactly what is the contradiction that you arrive to. If you what are the assumptions that you make in order to consider that you can assumptions that you make about how you're modeling the interaction. What is the contradiction that you reach? Like, I understand intuitively what you're saying, but that's a hand-wavy argument. I would like to see exactly.
Yeah.
If I make these assumptions, I get this, and this is not possible.
Yeah. No, I understand. Like for our case, the assumption is complete positivity, and then you're guaranteed to have these stochastic elements. For the reversible schemes, I can't speak for all of them because they also do different things. But in general, it's what you said, that you can't make it reversible. I mean, like.
No, I guess you're going to prove that, because if you're going to assume complete positivity, which you need in order to always keep having a quantum state, and then you'll see that there is no possibility, that it cannot be possibly reversible, then I think
that part will become clear in the talk. But the part that will not become clear in the talk is why every single linear theory fails. Because I think they're also set up very differently. There's theories that go back all the way to the 70s and 80s. And I think they fail at different stages, some earlier, some later. So I also don't know all of these particular details. But
thank you.
Yeah. Okay. So so actually, why is complete positivity the right choice here? And it's not so hard to see why we need something that's positive, because probability should be conserved, and the total probability should be conserved. So this gives you positivity and trace preservation. The reason why it should also be complete is because the quantum system may be correlated or entangled with an external reference system that we're not acting on. And then we also want our illusion to be such that it should still give a valid state even after adding such an arbitrary reference. And this is why you need this extra requirement of not just positivity, but complete positivity. And we already know the right mathematical tool for it, which is completely positive trace-preserving maps. And if on top of that you assume that you have some continuous time Markovian evolution, then the dynamics of classical quantum hybrid systems actually mirror the formalism of open quantum systems. And this is the key trade-off that I've already mentioned. So these completely positive schemes, they resolve the formal inconsistencies that you have with these reversible linear schemes, but they do so at the cost of then being irreversible, precisely because you have these stochastic elements, which you cannot avoid. And these are built into the dynamics. This is really analogous to open quantum systems. Okay, so the question is then, can such a scheme that is based on completely positive dynamics be something that could make a truly fundamental theory of quantum gravity? So the full master equation is rather dense, so I'm only showing schematic parts of this equation to focus more on the structure. And yeah, generally you should always think of this object as an operator value distribution, because this is really the difference from classical master equations. Apart from that, it's mostly analogous. So here you have two terms that are local in the classical phase space variable z. So these act on the quantum state with one fixed classical configuration. So we have this Hamiltonian term that gives you your usual quantum evolution, and a Lindblad term that takes into account local noise and decoherence, both at fixed z. And then the third term is fundamentally different. This is a term that is non-local. And here what you basically do is you sum over all previous classical configurations, which are called z prime in this notation. And then it describes stochastic jumps from z prime to z. Because your operator value distribution depends on these classical phase space variables, this can also change your quantum state, your classical quantum state. So you can think of each of these jumps, there's an associated quantum operation on the system. So this is, like I already mentioned, this is really the analog of a classical master equation. But the difference is really that your probability density is now operator valued. And okay, the notation is also kind of bad here. So this bracket is a commutator, but here the square bracket is because you have super operators acting on this hard row. And okay, maybe for completeness, I should also mention the full equation. It contains trace preserving loss terms and so on. But here I'm really trying to focus more on the bigger picture and the structure, and not so much on every little detail. Yeah, so the key point here is really that this non-local term, it redistributes your classical quantum state over the classical phase space. Yeah, and it describes classical jumps which can modify the classical quantum state. And a very natural way to analyze such jumps is to look at the size of the jumps by introducing this variable delta z, defined simply as z minus z prime. And this tells you that for a fixed initial value z prime, the non-local term, like this integral term, will then tell you exactly how likely it is to arrive at different final values of z. So this is actually a distribution over different jump sizes, delta z. And once you have that, you can actually recast this whole master equation in terms of statistical moments, which is done here. And again, the details are not so important. So this new thing that you see here, h mu nu, is related to the w from the previous slide. So I can show you a backup slide, maybe just to avoid confusion, how this exactly looks. So these are the full master equation, where again you have the separate Hamiltonian evolution, local Lindblad, and non-local transitions. And you can rewrite this in terms of this new kernel h mu nu. This is just a different formulation, and some of those terms have been absorbed in the integral, so it's a bit hard to see. But just trust me that those two forms are equivalent. And physically speaking, this h mu nu z z prime encodes the information from what was previously w. And I should also mention, so mu nu, they're not space-time indices here. They're labels for this operator basis, L mu, L nu. And these are essentially Lindblad operators. So technically, the things that you're familiar with as Lindblad operators would be linear combinations of these. But for practical purposes, they are essentially Lindblad operators.
And I guess this is guaranteed to have Lindbladian form because the W mu nu should be a stochastic matrix. Right?
Yeah. This is ensured by construction. It's basically my favorite kind of proof, which is proof by definition. All right. I think I was here. So here, the point of this equation is that your nth statistical moment will encode the nth order of this jump term. And you can then rewrite the master equation. And in our case, if we do this for the classical quantum system, then you will get three parts. You will get a part that's purely classical, a part that's quantum, and that evolves at, or that takes into account only fixed classical configuration Z, and the interesting part, which is this back reaction part, which I've written here. And this is where, you also have the zeroth statistical moment in the Lindblad term, but all the higher orders are encoded in this back reaction term, where this operator basis comes into play. So this is the only part that actually involves these non-trivial quantum operators, L mu and L nu. All right. So how do you actually interpret these moments? And actually, the zeroth term is the one that is different from the others because it has no classical derivatives. But because we know it appears in the Lindblad part of the equation, we know that this is the term that actually sets the decoherence and dissipation scale. For the other terms, it's actually more straightforward. So the first back reaction statistical moment appears with one derivative in the classical variables. So this is, if you're familiar with Fokker-Planck equations, this would be a drift term. And in phase space, a drift term is what you can interpret as either deterministic motion or a force. And in our case, we can therefore interpret this as the back reaction force that's exerted by the quantum system onto the classical system. Yeah, because these derivatives will be in the classical variables. And similarly, the second back reaction term, or the second back reaction moment, I should say, this is the standard diffusion structure where you spread your distribution in classical phase space. So this will be diffusion and or noise in the phase space. Now the key point is that these quantities are not independent, but they're actually constrained by this complete positivity condition. Because what you will have is you will have some coefficient matrix that contains these decoherence, back reaction, and diffusion terms. And then you can actually get a Cauchy-Schwarz type bound, which is the inequality that you see here. And this was derived in detail in this paper by Oppenheimer and collaborators. And what this tells you is that if you want to have non-zero back reaction, then these decoherence and diffusion terms are really unavoidable. So the back reaction cannot be deterministic and it cannot be noiseless in a framework that's completely positive. That's the takeaway message here. Okay, so far we've described this completely positive hybrid formalism on its own terms. And yeah, we've seen that it gives us a consistent way to describe back reaction at the cost, so to speak, of having the structure of open system dynamics with all the downsides like noise diffusion and stochastic stuff. Yeah, so again, the question is, can this be a formalism that's really fundamental, or does it arise as the reduced texture of something bigger, of a larger quantum theory? And in our paper, what we show is that there is in fact a way to embed this completely positive classical quantum dynamics into a theory that is fully quantum. So how does this construction work? And again, I'm omitting a lot of details here, but roughly speaking, it works like this. You first encode each classical label as an orthonormal basis state of some auxiliary register Z, so this will be a quantum register, and these pi Z are simply your orthogonal projectors onto the register basis states. And this will generate a diagonal commutative algebra that's associated with these classical variables. Step 2, you then represent your classical quantum state as a block diagonal state on this new system QZ using this new auxiliary register Z. And then if you want to show that you can recover the evolution of a classical quantum state, you can do this by showing that there exists a completely positive trace-preserving map on QZ that does exactly this, where when you look at it in the diagonal basis, in the basis of Z, you recover the classical quantum state if you apply this map. So this is this gamma T is the CPTP map on QZ. And yes, okay. And so the question is, what's the significance of this diagonal sector? And the reason it matters is not arbitrary. It's because your classical, so the way the construction works is that your classical observables are functions of the label Z. So in the register picture, they are diagonal observables of the form that you see here. So this would be this observable AZ written in the basis, and then this is just your value. So you can have in the classical quantum case some hat Q for the position, and then QZ would be the value of that position. Yeah.
Clearly the most general CPT map that is going to do this is a composition of a CPT map and a projection on the diagonal sector. Right? Can you show that this seems that, like, in general, it's going to be more general than the thing that you have, because there is no assumption about Markovianity. So I guess what you can definitely do is embed the evolution that you have on something like that. But then on the other hand, you could also see that there are maps that satisfy this, right? That are not of the form that you're assuming, because they might not be Markovian, right?
Yeah, so the Markovianity is actually already baked in, because, let me see, if you remember...
You assume it.
Yeah.
In your framework, I mean it the other way around. Like,
so the way you, yes, that's true.
Oh.
Yeah.
Okay.
So it's an assumption. If you assume continuous time evolution, that's actually what makes you get this open system dynamic structure. So yes, it's possible that there's something even more general that we have not looked at.
Okay, fair enough.
Yeah.
Okay. Thank you.
So I think I was somewhere here. Yes. Okay, and then what we show in the paper is basically that you can describe the evolution of your completely positive classical quantum system as the Z diagonal sector of the CPTP map. And yeah, this is true for, so in this talk, my notation is always discrete Z. But this is just to simplify the notation. In principle, you can actually implement the same idea in continuum phase space either by coarse graining into cells, or you just replace the sums of integrals, or if you want to do the projector way, then you need some spectral measure formulation. You can still implement those ideas. I'm only keeping this discrete notation because it's simpler for notational purposes. Okay, so now the question is, what is this classical quantum evolution that we actually want to embed? And this is where you see I'm sticking to the discrete notation because I'm using sums here rather than integrals. So again, as a reminder, this hat Q is the part of the classical quantum state associated with some classical phase space variables at some time t. And what this first equation, so this is, you might notice as a cross decomposition. And what this basically tells you is that the state at z and t you get by summing over all the previous configurations z prime in the different cross branches alpha. Yeah, and each of those branches will describe one term in the possible evolution from z prime to z. So these Krauss operators alpha q, they actually do two things at once. They label transitions from z prime to z, and they give you the corresponding quantum operation on the quantum subsystem. And yeah, we have the usual completeness relations and trace preservation. So this is, yeah, it's actually the analog of the usual classical cross completeness relation. So there's nothing new here. This just ensures that after summing over all final labels z and all cross branches alpha, your probability is preserved. And we've already covered the main equation. So what's the goal? The goal is to rewrite this transition rule from z prime to z into something that is a quantum channel that we can apply on the state that lives on qz. And we will do this by essentially replacing this transition rule z prime to z by a corresponding rule for the auxiliary registers. So, okay, I've already mentioned the two rules of the Krauss operators. What we want now is some rule for the registers that maps z prime registers to z registers. And then you can have a Krauss operator on the qz system, which is then composed of Krauss operators on the CQ system. So those are the ones acting on the Q subsystem. And this second part acting on the classical part, which updates your auxiliary register. And yeah, the small equation on the right here essentially tells you a way to read the definition of these channels psi alpha t. So if the register initially has some value z prime, then this map psi alpha will map it into some of a possible new register values z, and then that will live on the qz system. Yeah, and of course to do that you need the corresponding cross operators on CQ. And once we have these cross operators for qz, you can then define a channel acting on a state that lives on qz. And again, you inherit completeness relations from the normal classical quantum completeness relations. And this, yeah, I mean, what does this tell us? This tells us that we can represent this z prime to z rule by a channel, by a CPTP map on qz. So at this stage, the dynamics is actually represented as an ordinary quantum channel. And this classical quantum interpretation, it reappears only when we will restrict to this diagonal z readout, which I will show in what follows. So what we have to show now basically is that when we look at the diagonal z blocks, we should recover the original classical quantum evolution. Right. So we can consider an initial state which is block diagonal in the z basis, looks like this. And yeah, these blocks labeled by z prime, they will contain these operators at time 0 because we're looking at the initial state. And then we can apply the QZ channel and look only at the diagonal block labeled by Z. And again, you get this by summing over all the previous labels Z prime and all the cross branches alpha. And what you will find is that actually this has the same representation as the classical quantum transition rule. This is the exact same structure. And it gives you your classical quantum state. So the Z diagonal block of this evolved initial state is precisely the classical quantum state at some later time t. Right? So we have this evolution CPTP map on QZ. We apply it on the initial state, look at the Z basis, and we get the classical quantum state Z at time t. Now, another way you can do this is by defining a pinching map, PZ. So this is an operation that keeps only diagonal Z blocks and removes all of the off-diagonal blocks, which I've represented schematically here. So if you throw this pinching map onto your previous expression, then you will get this diagonal matrix, which is your CQ state, and you will have one diagonal block for each classical transition Z prime to Z. And then after you perform this operation, the state will again have this embedded classical quantum form where you have one diagonal block for each classical label. So the embedding actually works in a very concrete way. You evolve the ordinary with an ordinary quantum channel on QZ, then you read off the Z diagonal blocks, and then these blocks actually reproduce your classical quantum dynamics. So I want to add one more slide to explain why you can actually ignore these off-diagonal Z blocks. And it's because it's not an arbitrary projection, but it is precisely the projection. So these operators are very special PVM elements, namely precisely those that restrict the Z observables to this classical readout algebra. Okay, I should have probably switched to this slide earlier because this is what I was just saying. Yeah, so this is still, it's important to keep in mind this is still quantum. The registers set are quantum, but we do not have arbitrary access to the quantum register Z. So if Z is supposed to be a classical variable, then the observables with Z will decompose in this form that you see here. They should be functions only of Z. And because of that, in the register language, they will be diagonal observables. And because of that, they will commute with each other. And again, these numbers AZ are just the corresponding classical values that you would have. So this tells us that the accessible Z algebra is actually classical. Another way of seeing this is to consider some general state that lives on QZ, which may have off-diagonal blocks in the Z basis. But then if you measure only observables of the form AQ tensored with AZ, which are diagonal, then the expectation values will depend only on these diagonal blocks with respect to Z. So the off-diagonal blocks never actually contribute. So this is just a different way of seeing this. And of course, you can again rewrite this in terms of this pinching map PZ. So what this equation then tells you is that this pinched state where you apply the pinching map on X and X are actually indistinguishable by any of the allowed classical quantum observables. So again, the point here is that this diagonal projection is not arbitrary. It's not an arbitrary deletion of information, but it's precisely the part of the QZ state that is invisible to the classical readout. And yeah, in this sense, the Z sector is operationally classical. So it's not because Z is not quantum, it is, but it's because access to this auxiliary register is really restricted to this commuting readout algebra. And before continuing, I want to make it clear that this is not a canonical quantization. So in canonical quantization, typically you promote your phase space variables to non-commuting operators. But here this is clearly not the case because our classical readout variables, they commute, right? And this is simply because our registers, they store both of these phase space variables as a label, and both of these are diagonal functions of that same label, so they will commute. So just to preempt any misunderstandings, this is not quantization in the canonical sense. Right, and because it's not canonical quantization, it's not directly related to canonical gravitational degrees of freedom. Okay, so this also, it does not mean that the construction is not quantum, because the evolution on QZ is still, it's an ordinary CPTP quantum channel. And what you can actually do is you can use Stein-spring dilation to represent this as a unitary evolution of a still larger system, where you have this, usually people call it ancilla, we call it E for environment. And then, sorry, excuse me. And yeah, then you will see precisely that you can rewrite this channel acting on the QZ state as basically what you would get if you traced out the environment of something that is Stein-spring dilated. I feel like I forgot to say something on this slide, but I can't think of it right now, so maybe I'll get back to it later. Okay, so let's talk about what's the physical significance of this embedding result. Well, it shows us that these completely positive classical quantum theories need not be irreducibly hybrid. And how do we know this? Well, we know this because we can obtain the classical quantum state by first applying an ordinary quantum channel on this enlarged system QZ, and then keeping the diagonal Z sector through the pinching map. And this last equation on the previous slide goes one step further and shows that you can actually obtain this, this description with this CPTP map gamma T by tracing out the environment if you do a Stein-spring dilation. So at the level of mathematical representation, the dynamics does not have to be irreducibly hybrid. So this embedding result shows us that you can actually realize CP-secret dynamics inside of a theory that is fully quantum. What it does not show is whether or not this is actually a fundamental theory, or if it can be a fundamental theory, or if it's only an effective or reduced description. And the second point, which I've highlighted because it'll be the focus of the remainder of the talk, which is also not clear, is whether or not conserved quantities of the full dilation will still appear as conserved observables after tracing out the environment and restricting to this diagonal Z readout with the pinching map. Right. So the point of considering this even larger dilation with the Stein-spring dilation theorem is to show that you can realize this CPTP channel gamma T on a larger quantum system QZE, followed by then tracing out the environment. So this is also another indication, so to speak, that CP-secret dynamics can be interpreted as a reduced sector of dynamics that is fully quantum, rather than something that is irreducibly hybrid or inherently classical. Okay, my laptop is stuck. No, there we go. Okay, so let's talk a little bit about the last point I've mentioned here. How does this affect conservation of Noether charges? And in closed Hamiltonian, 5 minutes? Okay. So in closed Hamiltonian dynamics, there's a very familiar form. If you have an observable that commutes with your Hamiltonian, then the expectation value of that observable is conserved. So again, notation is a bit sloppy, but I think you're catching my drift and know what I mean. So this is the usual Hamiltonian version of the intuition of Noether's theorem. In completely positive dynamics, the situation is a bit different because the condition for conservation involves this Liouvillean L, and yeah, actually the observables are conserved exactly if for all states the if the observable lies in the kernel of this adjoint generator L dagger. So this condition is actually much stronger than the condition we have for usual Hamiltonian dynamics. Yeah, so it's also much more specific than just saying that your equations of motion are symmetric. And we will see that this tells us that symmetry is actually not enough in the CPCQ case to ensure conservation of conserved quantities. So in this case, symmetry really means covariance of the dynamics. And I think I've already said this part, symmetry does not guarantee that you conserve the generator G. It's only conserved if this equation holds. Okay, so I only have a few more minutes, so I will briefly consider a toy model, and I will skip through this a little bit. The simplest closed classical quantum model that you can think of with rotational symmetry is just a qubit coupled to a classical particle. Your qubit you can describe with the Pauli matrices. The spin will be defined in terms of these matrices, and your classical particle will usually have some positions and momentum components. And because of that, in general, also angular momentum. So your classical quantum state will be a two-dimensional density matrix, which again, it'll depend on these classical phase-space variables. And yeah, component-wise, your total angular momentum will have two contributions, this classical angular momentum component and the qubit component, which is this spin part here. Now, is this total angular momentum conserved if the equations of motion are rotationally invariant? Yeah, to answer that, you can choose an evolution that has no preferred spatial direction. So classically, you do this by looking at something that is just a rotationally invariant distribution, which depends only on these variables. And for the quantum part, you can do this by simply summing over all three of the Pauli matrices. So this ensures that there's no preferred spin axis. And yeah, so this equation is rotationally invariant under joint rotations of both classical variables and the qubit spin. But it's not Hamiltonian or unitary, but it is completely positive. So yeah, it turns out that this particular construction, your dynamics is rotationally invariant, but as I said, evolution is not Hamiltonian or not unitary, and because of that, yeah, you will actually find that in general you do not conserve angular momentum. You can solve this equation exactly. You will have a part here that corresponds to basically the part of the initial classical quantum state that survives with this exponentially suppressed weight, and relaxation to rotationally invariant stationary state, where there's no preferred axis, both in the classical and the qubit system. Okay. Let's see, I'm just trying to check how many more slides I have for the 2-3 minutes, and if I should maybe skip them. Okay, but let's take things step by step. So to make this loss of angular momentum explicit, you can choose a stationary classical distribution concentrated at Q0 and P0. This is rotationally invariant, and then it will carry no angular momentum. And the stationary state is maximally mixed, so it carries no spin angular momentum either. And yeah, if you do that, then again, your where is it? Oh, sorry, it's on the next slide. Oops. Sorry, I'm like zipping through all the wrong slides now. Right, okay. So points to keep in mind here, both pieces of directional information are suppressed by this exponential factor, and the final stationary state contributes no angular momentum. And this is why your total expectation value decays with this exponentially suppressed term. And in the long time limit, this will go to 0. And this shows you that even though you have rotational symmetry, you do not conserve angular momentum in this system. It's also not extremely surprising because you have the structure of open system dynamics where you have dissipation. Yeah, so maybe it's not entirely surprising to you. Okay, Now, what's the point of this, or the lessons from this toy model? It's not to model gravity directly, but it's to isolate one of the structural issues that you have with these completely positive schemes. So what we showed is that when you have a closed classical quantum system with completely positive dynamics and rotational symmetry, you do not, in general, conserve angular momentum. It'll decay exponentially. And the lesson here is not simply that this particular model loses angular momentum, but this is really a broader structural feature of completely positive dynamics. That symmetry of the equations of motion does not by itself guarantee conservation of the associated Noether charge. There's also an important caveat, which is that a toy model is not a fully relativistic theory of classical quantum gravity. So you could say maybe once you should examine this separately, maybe in the relativistic case, these issues can be fixed. So for classical quantum gravity, this is not a no-go theorem, it's more of a slight warning that you should, and also motivation that you should check the fully generalistic theory to see if it resolves those issues. But the mechanism does matter because if the reduced classical quantum sector contains things like relaxation, decoherence, and diffusion, that means our usual conservation laws are not automatically protected, even if the equations are symmetric. And tying back to testing things in the lab, this actually ties back to phenomenology, because if you do not observe relaxation over a time scale capital T, then you should expect a bound on this dissipation decoherence scale kappa of 1 over T. And because completely positive dynamics ties this to back reaction via this inequality, if you have such bounds on kappa, you can then also derive bounds. So this would give you immediately bounds also on the back reaction and the diffusion coefficients. Okay, I will stop here with the summary slide. So the one-sentence summary here is that we've shown these classical quantum gravity theories may actually just be quantum gravity with restricted axes, because there's no way to make sure that the stochastic parts of the classical sector of this theory do not have an origin that is fundamentally quantum. And with that, if we have time, we can open the floor for questions. If not, I'm happy to discuss it later. Thank you. Yeah, I'm sorry for going over time a bit, if I did.
I can't complain. I mean, we can open the floor for one quick question. Yeah.
Thank you for the talk. I'm a little bit concerned with the conclusion that because you can represent something on a Hilbert as operators on a Hilbert space, you're quantizing. Because it's about, for me, quantization is more about whether you have irreducible representations of algebras that are not commutative. In this case, I don't see any distinction in the conclusions from trying to say that you quantize a classical theory because you represent it as operators in a Hilbert space. So is there any difference in this case that makes the conclusion stronger in the hybrid classical quantum thing? Can you say that you're actually quantizing the degrees of freedom of gravity, or like not the gravity, or like the classical part of the dynamics, just because you're representing them in a Hilbert space?
Yes, good point. And the answer is no. So this is precisely this slide, which says we're not doing a canonical quantization. So you cannot infer anything about canonical gravitational degrees of freedom here. The statement is simply you have a classical quantum theory, and the classical part is stochastic. But what we show with this embedding result is that if what we basically show is that there's no way to rule out the possibility that this stochasticity in the classical part has an origin that is fundamentally quantum. This is what the embedding theory shows, what the embedding theorem shows, but it does not tell you anything about canonical quantization or about canonical gravitational degrees of freedom.
Can you repeat it? That doesn't show what?
It does not tell you anything about canonical quantization, because that's completely different. Here you have phase space variables that are promoted to non-commuting operators, which is not the case in our embedding. So our embedding does actually not allow you to make any statement about canonical gravitational degrees of freedom.
Okay.
I plugged in my computer.
Okay, but what it does show is that there is no way to ensure that the stochasticity in the classical part does not have an inherently quantum origin.
Okay.
Because if you embed it in a larger system that's quantum, you can show that you get precisely these stochastic parts that you have in the classical case.
So, but then if I give you a Brownian particle, a classical Brownian particle, you also don't have any way of knowing if that doesn't have a quantum origin, right?
Yes, that's true.
any classical system. I mean, I think, if I can interrupt, because everything is based on the pinching map, which is really a projection on the subspace that is diagonal on the states that have your classical label. You can literally always do that. What the unitary is gonna do is that there's gonna be this map that basically has the cross operators and then has a copy of the classical label on the environment part, and then you trace it out, and then it implements the projection. So yeah, I think this is generic. You can always do that with a classical system.
Yeah. So I think basically the point is it's indistinguishable. This classical sector is indistinguishable from something that is quantum, but restricted to this.
What I would call quantum is not the fact that you can represent it as an operator, operationally.
Yeah, because classical physics is the h bar going to zero limit of quantum mechanics in which things commute, right? So it's I agree.
Yeah, but this is not the same. That is because it's not taking a limit in which things commute. This is projecting. This is a projection onto the subspace. No, but if you go back
to the previous slide of the commentators there, it's literally like what you're saying is that the thing on the right here, right? It's literally. It is the canonical gravitational degrees of freedom in the limit of h bar going to zero of that side only. No,
right? That's the point. That's not true. I don't think it's true. I don't know if you agree.
I also don't think it's true. But if
the operators commute, right? It's like, of course, not just the thing going to zero, but it's if you only have commuting operators, what's the difference between classical and quantum mechanics?
But putting the mathematics aside, think about it in terms of physics. You know this classical sector has some stochastic elements. Where do those elements come from? It's completely unclear, right? Mm-hmm. But here you can see where they could come from. And they could come from a quantum sector that is just access restricted, in a sense.
Yeah. There could be many.
Yeah, no, this is not unique, yeah. Yeah.
Okay, let's thank Sebastian again.
Thank you.
And our next and final speaker is Bruno Torres.
Sorry, I think this is gonna drop.
Yeah, you can. Yeah, you can. But you need it or you can't? Do you have HDMI?
Yeah.
Okay, sure.
Do you want a pointer or no?
Yeah, leave it here. Is that yours or?
It's mine, yeah. But pretty useful.
Sebastian.
Oh, sorry. I've kidnapped the microphone. Oh, sorry. Is this like clipped or?
Oh, sorry. Let's click this.
Here we are. What is this? Oh, address. Okay.
Is that comfortable?
There.
Not too much. Well, you can adjust it.
Should be better.
Perfect. Okay, then, well, as I was saying, last talk of the session and the circuit, or this session of the circuit at least, it's going to be Bruno Torres, who's right now based in Ghent University. He's going to talk about quantum effects on local observers in JT gravity. Bruno, the floor is yours.
Thanks, Jose, for the introduction. It's a pleasure to be here spending this time with you. I'm the only thing standing between you and lunch, so I will be brief. Without further ado, let's go. So, you have time. I'm going to talk to Yeah, I know, but I'm tired, so. Okay, so the motivation, like the big picture idea behind this project is this conceptual problem that we have in quantum gravity, where if you want to talk about the experience of local observers in highly quantum regimes of the gravitational field, there are some fundamental obstructions to doing that. One way to formulate this is to point to the fact, for instance, that in complete theories of gravity with dynamical gravity, the gauge invariant observables must be diffeomorphism invariant. And this generates obstructions to our usual idea of how to define locality. And what this means in turn is that the definition of what we call local observables and in turn local observers becomes a part of the dynamical degrees of freedom of the theory that should be defined in terms in particular of the gravitational degrees of freedom as well. And the ideology I'm promoting here is that it is useful to have explicit toy models for these kinds of things in fully solvable models of quantum gravity, which you can achieve, for instance, in lower dimensions, just as a testing ground for effects that you can extract beyond the semi-classical regime. So what I will do today is to describe what I'm calling a gravitational addressing of bulk observables in a solvable model of quantum gravity, namely JT gravity, which I will review in a second. I will use this choice of gravitational addressing to define a notion of local observers that makes sense and also includes quantum effects of the gravitational field. I will then use that to show an example of something that you can compute. For instance, the response of a particle detector falling into a black hole. And if we have time and energy at the very end, I can explain another application of this to study non-perturbative effects on the thermal atmosphere outside of black hole horizon, also in this model. So just a quick recap on JT gravity. So JT gravity is a dilaton gravity theory in 2 dimensions. The ingredients on the classical action are the 2-dimensional metric, dilaton field, and the action contains a bulk term that depends on the Ricci scalar of the metric, and also a boundary term that depends on the extrinsic curvature of this boundary of the spacetime you're considering, as well as a purely topological term, controlled by this parameter S0 times the Euler characteristic of the manifold. If you think of this as coming from higher dimensional reduction of higher dimensional GR, this action emerges if you expand the Einstein-Hilbert action around extremal black hole solutions, and from that point of view, this parameter S0 is the extremal black hole entropy, or the Bekenstein-Hawking entropy of the extremal black hole around which you're expanding the action. And this topological term does not play any role classically because it's just a topological term, but it will be important in quantum gravity once you include some other topologies, and if I have time, I'll explain exactly where this can become important in a concrete observable. So the strength of JT gravity, so why you should be at least mildly interested in what JT gravity has to say about anything, can be explained by 3 arguments. The first is, well, it describes the near horizon physics of near extremal black holes in higher dimensions, so people can try to extract predictions on more realistic, so to speak, black holes in the sense that they live in 4-dimensional spacetime. So that's one thing. They also encode an effective description for the low energy sector of a family of quantum mechanical models known as the SYK model. And in that sense, they are a concrete example of holography in 2 bulk dimensions. And that is particularly interesting, at least for some people, because SYK is something that you may be able to efficiently simulate on a lab. So that's like a concrete example, as close as we can get in the near-term future of a test of ADS-CFT or something of that sort. And the main reason why I'm advocating for this right now is that it is analytically solvable. JT gravity, as a theory on its own terms, is analytically solvable both classically and quantum mechanically. And so it can be used as a toy model to study quantum gravitational effects beyond the semi-classical regime. So just as this will be a quick recap of what we did on Wednesday, but just so that everybody's on the same page. The dilaton field appears in the Lagrange as a Lagrange multiplier, and enforces that the local metric is a patch of ADS. We can parameterize ADS in Poincare coordinates, and then the only degree of freedom that remains in the action is effectively the trajectory of that boundary, which contributes to the action via the Gibbons-Hawking term. And in a limit, that would be the limit I will consider, the full dynamics reduced to just this Schwarz action that depends on this function f. And the function f determines the shape of this boundary curve in Poincare coordinates parameterized like this, where epsilon is a UV cutoff that you usually take to 0 implicitly. So in the two-dimensional picture, what you have is the Poincare patch of ADS, and you have this boundary curve controlled by this reparametrization from this boundary time t to Poincare time tau. The higher dimensional picture is that this ADS region really describes a throat in the near horizon region of a near extremal black hole that is connected to an asymptotically flat region outside. And the gluing between these two regions appears in this effective boundary, which from the higher dimensional point of view is where the Schwarzian kind of lives. And then the JT gravity description applies in this ADS2 throat. So when you read papers that do JT gravity, they might call the things that they describe effects on the quantum throat of black holes. That's where the jargon comes from. But for this talk, you can just forget all that, and we'll just talk about JT gravity as a theory in its own right. Just if you want to keep the motivation at the back of your mind, that's where it comes from. So things that we can compute that will be relevant in the rest of the talk in JT gravity are things such as the thermal partition function of ADS2 black holes. This can be parameterized by a diffeomorphism on the circle that comes about because of the Euclidean periodicity condition when you compute a Euclidean partition function. This can be computed in full, and the result is this. And from that, you can infer the density of states of this putative theory that describes the black hole at the quantum level. Something else that will also be important for what I will do is something that we call in the Schwarzian theory the Schwarzian bilocal. The definition in terms of the Schwarzian is this, where this big F is the map from boundary time to Poincare time, and from here to here, I use the thermal reparametrization in Euclidean time. The physical motivation behind this guy is that it should be understood as the boundary limit of a bulk scalar field as you take it to the Schwarzian boundary. The expression that you get in the end will be of this form, where this delta is the conformal dimension of the field that encodes the mass of the scalar field in the bulk. Diagrammatically, people will draw pictures like this to represent what this two-point function is in Euclidean signature. And I'm bothering to explain this to you because this also has a closed form expression that is exact at the level of the Schwarzian. Okay, so the recipe to solve problems in JT gravity is very simple. You find what the dynamical degrees of freedom are in your problem, and you translate them to the Schwarzian. You look at the observable of interest that you want to compute, and you express it in terms of things that you know how to compute, which secretly are only Schwarzian bilocals. And that's what it will do. And then after that, you become rich and famous, ideally. Okay, so let's see how this plays out for this idea of gravitationally dressing bulk observables in JT gravity. So, as we said in the introduction, diffeomorphism invariance kind of forces you to consider relational definitions of local observables in terms of other dynamical fields of your system. And yeah, this is what I just said. The idea is for everything to be invariant under diffeomorphisms, and the relation between these gauge variant observables is what is preserved by diffeomorphisms. And another way of phrasing this is just that this is what I mean by gravitational dressing, where the gravitational aspect of this is that the relational degree of freedom is defined as a function of the gravitational observables, obviously, or degrees of freedom. In JT gravity, the only gravitational observable that you have is the Schwarzian mode. So the question is very natural now. Is there a way to pick a preferred recipe to dress bulk points in ADS2 to the Schwarzian, encoding the boundary trajectory, so that the Schwarzian now no longer describes only a boundary trajectory, but ideally a whole bulk frame in the interior of your spacetime. And this is the first thing that we will achieve. We will come up with a way to justify a family of local observers defined by this dressing. that probes the exterior region of ADS2 black holes. And the ingredients will be the following. First, we want the observer world lines to foliate the exterior of a classical black hole. So this will be playing the role of the static observers. So the orbits of the Schwarzschild time-like isometry, for instance. The world lines should asymptote to the Schwarzschild curve as we approach the ADS boundary. That's just to say that they truly extend the boundary trajectory into a vector field in the bulk. And this is the key ingredient now, that they should be such that they form a conformal killing vector field in the bulk. If you do these three things, turns out that there's a unique way to map the Schwarzschild to the bulk. And intuitively, the answer is very simple. You go back to that description of the Schwarzschild in Poincare coordinates. You have the light cone coordinates of the Poincare patch. And for any off-shell profile for the Schwarzschild, you map U as f of u and v as f of v, where u and v are boundary times of the Schwarzschild curve. And from this, you define an effective radial coordinate that is just like the time coordinate in the bulk is just the average of these two boundary times. And the bulk radial coordinate is just the difference between these two boundary times. A more intuitive way of seeing what this is doing is a picture like this. The geometric interpretation is very simple. You're labeling bulk points by boundary times, which are fixed. This is the thing that is in the quantum mechanical description of your system. So your boundary curve will emit a light ray at boundary time v and receives another signal at proper time u. You will label the bulk point by the intersection of these two light rays, and this will depend on the Schwarzschild through the embedding from boundary time to Poincare time. The effective radial position of this point is then just the average of these two boundary times, which is, a relic of this, Einstein antenna construction of bulk frames, now adapted for any profile of the Schwarzschild. So here is a picture that you might have to take into account that this Schwarzschild can fluctuate. So for each boundary Schwarzschild profile, you have slightly different curves here. And that will encode quantum fluctuations, let's say, of your gravitationally dressed observer. And these curves are supposed to represent the static observers with respect to one particular choice of Schwarzschild. Now, this dressing has been proposed before as a way to construct bulk frames in JT gravity. The thing that we did in the recent work was to derive this from something that I think is well motivated, which contains this ingredient that the boundary time translation should be extended into the bulk as a conformal killing vector field. You may ask why this is a good requirement to have. Why should I care about conformal isometries? And the short answer is because they present a special connection between diffeomorphisms and geometric modular flow. So this is a story that is too long to explain, but the short version is recent developments in quantum gravity have made use of this construction relating the algebra of local observables and a mathematical procedure called the modular cross products in phenomenon algebras. This is most easily motivated by noting that this modular cross product algebra that you construct implements diffeomorphism invariant observables if the generator of the modular flow that you used is geometric. So if there is a diffeomorphism in the bulk, that can be interpreted as modular flow by some state. And a necessary condition for a modular flow to act geometrically on some bulk manifold is if this diffeomorphism is a conformal isometry of the background geometry. So if you look at this final point, essentially what we did is to show that the only gravitational dressing at the Schwarzschild level that has any chance of being mapped to a geometric modular flow is this that we just defined. So yeah, I think this is a strong motivation to care about what we're doing. Now, with that in mind, let's apply this to some interesting physics, namely the response of a gravitationally dressed infalling detector, which is something that would be very familiar to many people in the audience. So the setup will be, again, a particle detector coupled to a massless scalar field in an ADS bulk. So we'll consider a massless scalar field in ADS2, take the Poincare vacuum. And the vacuum two-point function in closed form is known, and in the black hole patch, where the line element looks like this is the form of the Weidmann function. Or, if you prefer, this can be written also in the Poincare patch, like this, where I recall the line element is written like this. And you can obtain the previous expression from this one by just using the thermal parameterization of the light cone coordinates that take you from the Poincare patch to the black hole patch. Okay, now we play with our gravitational addressing. Everything there was classical. Now you make those points functions of the Schwarzschild, and you do this cute little trick to express this two-point function as a double integral of this guy here. The reason why we care about this, if you remember, this thing looks like the Schwarzschild bilocal. And then you can restrict to the black hole patch by just playing with the same substitution we had before, where now you replace this big F with this small f, which now labels the dynamical trajectory of a boundary curve that is restricted to lie in the black hole patch. The same trick now will express the two-point function like this. This is the Schwarzschild bilocal in Lorentzian signature in the thermal parameterization. So you now understand this whole thing as a function of the gravitational degrees of freedom, and you can compute the expectation value of that in the quantum gravity theory. So it will be something of this form, where this thing has a closed form expression. Here, I'm writing it in Lorentzian signature. Here, this thing is defined implicitly in Euclidean signature, but it can go from one to the other, just with rotations. So this function was defined in the exterior of the black hole. You can also extend it to dress points in the interior of the black hole. If you now, instead of playing with this game of shooting light rays to just one boundary, you dress points in the interior with two path-directed light rays. And then instead of your point being labeled by 2 times in one boundary, there will be 1 time in one boundary and 1 time in the other boundary. And the Wick rotation trick that you use now is just to map these two boundary Schwarzschilds to the Euclidean Schwarzschild variable, like this. So there's a field redefinition here to go to the second boundary. This is like moving in the Euclidean circle like this, plus the Wick rotation and analytic continuation of the quantum mechanical time at the boundary to describe the thermal field double state. And in practice, what this means is that the correlation functions containing gravitationally addressed points in the interior and the exterior are now obtained from the one-sided correlation functions just by analytic continuation, as in any two-sided thermal state, or in the thermal field double that purifies any thermal state. Okay, now to probe these correlations, we'll use the favorite tool of anyone who does RQI. We just plug an Arrow-Dewey detector and make it fall into the black hole and see how the detector reacts. To simplify our lives, we'll imagine that the Arrow-Dewey detector follows a null trajectory, and the interaction action is given by this form. The coupling constant I'm labeling by Q because lambda is already something else. Lambda is the affine time of this bulk trajectory. Chi is the switching function. The monopole operator appearing here is just the sigma x, as usual. And the tangent vector is now just derivative along this null trajectory with respect to affine time. With that, we can compute the excitation probability of the detector. This is just the most well-known thing in this audience, probably. This will just be a double integral containing the switching function, and because we use derivative coupling, the derivative of this two-point function. And for concreteness, we'll pick the switching function to be a Gaussian because that will have a nice semi-classical limit. And what we're interested in looking at is this excitation probability as a function of the parameters of the problem, in particular this lambda 0, and the temperature of the detector, and the temperature of the thermal field double state. Now, this is all written in affine time, right? To do the computation, it's convenient to go back to the coordinates of the black hole patch that we had. To find this lambda as a function of the original coordinates, you just look at the line element again, and you ask what is an affine time for curves of constant v in this case. If you know that this is just a conformal or a Weyl transformation on this line element, you can see that the affine time and affine time lambda and boundary time u along surfaces of constant v is fixed by this relation. And then you can compute this because you know the expectation value of this guy. Now, in the full quantum theory, this should be seen as defining an operator in the Schwarzschild theory. So when I take the expectation value, I'm really defining the evolution of this expectation value of affine time as a function of this boundary time. And in what I'm about to do, I will assume that when you go close to the horizon, fluctuations of that guy are suppressed sufficiently fast, which you can check by, again, computing fluctuations of this Schwarzschild bilocal. Just to give a more familiar flavor to this, right? If you do QFT in curved spacetimes, you don't make the Schwarzschild dynamical, you just use the saddle point approximation in the thermal reparameterization. This is what happens, right? This was the conformal factor in the thermal reparameterization. The solution to this is just something like this, which at very late times just decays exponentially. If you write down now the derivative two-point function of a massless scalar in terms of affine time, what you get is this. So this takes the same form as the two-point function of a massless scalar in 3 + 1 dimensions. So if you integrate it with a Gaussian switching function, you know what the solution is. It's just something like this. The features that I want to highlight here are that this excitation probability is independent of lambda 0, the center of the Gaussian that we picked. This should be obvious because the two-point function is time translation invariant in lambda. And it is also independent of beta, this parameter in the temperature that we picked. And this is true, morally speaking, because this state that we defined, right, the switching function that we defined, is the global vacuum in ADS2, so it doesn't really depend on beta. Beta was, in that case, was a coordinate artifact of picking one particular patch to define your coordinate system. And the perhaps surprising thing is that when you couple to the dynamical Schwarzschild, these things will cease to be true. So you will see observable effects that depend on lambda 0 and on beta. And this all boils down to different behavior of that Schwarzschild bilocal at very late times. I'm interested now in the case where the probe is close to crossing the horizon. In terms of boundary time, that's always u going to infinity. So the Schwarzschild bilocal, let's say, I should have inverted the order of these equations. So the expectation value of the Schwarzschild bilocal is no longer exponential at very late times. It goes like a power law. And if you use that to relate the affine time, or the expectation value of the affine time of this infalling probe with boundary time, you get this power law again, where this A, this constant here, is given by this. And similarly, so now I defined this lambda u in the exterior of the black hole with the boundary condition that lambda = 0 corresponds to the horizon crossing moment. If I now extend that to the interior and match those two, the affine time in the interior for very early times of the route boundary goes like this. If you just plug this back now into the gravitationally addressed two-point function, now expressed as a function of affine time, you get some nasty expression like this. And now you just ask your favorite numerical method to compute the excitation probability that you get from that. And the results qualitatively look like this. So this at the top is the excitation probability normalized by the coupling constant squared as a function of lambda 0. So the moment where the Gaussian is most strongly peaked. You see here that there's definitely a lambda 0 dependence. So the system ceases to be translationally invariant. And in particular, the peak is at lambda = 0. So the detector can tell, let's say, when it crossed the black hole horizon by testing when this excitation probability is peaked. And you can see also that this is plotted for different values of beta. And the excitation probability grows when beta grows, which means if you take lower temperatures, the excitation probability is higher. And in the right-hand side here, just have a plot of this probability as a function of the inverse temperature, where I picked lambda 0 to be the maximum of this plot. So the conclusion here is that this gravitational addressing allows you to detect the horizon locally, because you can just shoot an array of detectors that couple to the field at a fixed time intervals in affine time, but at different times, and then you can tell where the horizon is. And you can also infer what the temperature was for the same reason, because the height of this peak depends on beta. Now, just a quick comparison with the semi-classical results. Again, this is just a plot of that analytical expression that we had. This is the numerical result that you get with a certain choice of parameters here. And the thing I want you to pay attention to in this expression, these were all plotted with the same size of parameters, is that the order of magnitude of these excitation probabilities is quite different. This is about 10 times more than this. So for fixed coupling constant, the excitation probability is much higher in the Schwarzschild dressing than in the semi-classical expectation, which shouldn't be a surprise because you are including a degree of freedom that is also fluctuating. So that leads to more noise. The probe has a higher chance of getting excited for any finite time interaction. And this is also consistent with the previous plots because you know that Schwarzschild fluctuations become stronger as you lower the temperature, which is what we saw in the previous plot. So, yeah. This is a story for the en route wave detector falling into the black hole. Now I'm gonna shift gears and explain another application of this whole story to talk about the thermal atmosphere in quantum JT gravity. So the idea here is we can consider a two-dimensional CFT minimally coupled to gravity. And we play again the same game. We write down the line element as a function of the Schwarzschild using this dressing. And now the question we ask ourselves is, for a fixed value of this bulk radial coordinate z, you take the reduced state of a 2D CFT restricted to live between the boundary and the bulk point in the interior labeled by a fixed value of z. And it's a result from two-dimensional CFTs that this entropy is fully fixed by the conformal by the Vidal transformation between essentially this line element and this with the conformal factor. The expression can be repackaged like this. And if you remember, this should be familiar to you at this point. I'm just repeating the equation again here. This thing that appears in the argument of the derivative is just the derivative of the Schwarzschild bilocal with respect to the conformal weight. If you plug that into the Schwarzschild path integral, you close your eyes and move forward, you can compute that once again because you know exactly for any value of delta what this looks like. Okay. Yeah, this I just replaced that thermal expectation value with its closed form expression in the limits of this bifurcation surface being very close to the horizon. You can evaluate this nesting integral exactly using suitable approximations, and the result that you get reduces to just this linear growth in Z, which is just the volume law for the thermal entropy of a CFT in one spatial dimension. So the conclusion here is that the Schwarzschild path integral with the Schwarzschild dressing of the bifurcation surface does not change the semi-classical expectation for the thermal entropy of the thermal atmosphere as seen by static observers. But now we can do more because JT gravity is not just a Schwarzschild. We can also now play with higher genus contributions coming from the gravitational path integral with arbitrary topologies. And what I promise you is that this will also qualitatively change the nature of the black hole horizon. Now here I'm going to introduce some more machinery, so I think this is a good place to ask if anybody has questions. Shall we go?
Can you recover this? And you showed before in the previous section that there is very big difference between the Sharpsham prediction and the semi-classical limit.
Yeah.
What is the regime in which you recover the second? Is there like some lambda zeros? If you pick your...
Yeah. So in this parameterization, so the thing, I can go back. So what you need to look at is this parameter here, this regime. So this is boundary time, and C is the Schwarzschild coupling, right? Which in the semi-classical limit goes to infinity. What you have to check now when you plot those, when you do those plots, is if that lambda 0 is such that this thing, or if you invert this, you write u as a function of, u minus v as a function of a and lambda 0, whether that is still within the regime of validity of this approximation. And that will give you an upper bound of that lambda 0 and that sigma. And that upper bound decreases as you send C to infinity, which is as it should, because it means that you have to go closer and closer to the horizon, so consider later times before you see deviations from semi-classical.
So the calculation that you have is in a like in a complementary regime
to the semi-classical, yes.
There's not a region where they coincide. It's just that when you take the semi-classical limit, the region where the other calculation is valid is just
exactly. So if you imagine keeping track of the entire evolution of this infalling probe, what will happen is there's a regime where this Schwarzschild expectation value converges to the semi-classical expectation. So instead of being a power law, it's an exponential law with the right exponent. That regime is precisely when this u minus v is between beta, so the thermal scale, and the C, right? So that assumes a sufficiently hot black hole, because that assumes that beta is much smaller than C. If beta is much smaller than C, then you'll have a regime where the semi-classical prediction applies, also in this case. If it's a very cold black hole, so if beta is much larger than C, then you will never have that semi-classical regime, which is another way of saying that quantum fluctuations at low temperatures will dramatically change the semi-classical physics. Okay, so where were we? Okay, this is the semi-classical prediction for the entanglement entropy of a segment of a 2D CFT in the exterior of the black hole. But now I'm saying that we can also do better and include higher genus effects on this. And to do that, we'll have to add some new tools. So the big picture statement is that higher topology effects in JT gravity can be included. And what they amount to is completion of JT gravity as a matrix interval. And this will be mainly pictures now, so I hope the qualitative features are clear. The idea is the following. Imagine you want to compute this partition function. So you start with some circle of parameter beta, right? And when you do gravity, right, if you believe in holography, the thing I will do is you will fill in the space bounded by the circle with a bunch of two-dimensional manifolds. You can include a genus 0 surface, genus 1, genus 2, blah, blah, blah. If you remember that full action with the topological term, that Euler characteristic for these surfaces would just be 2 minus 2g minus n. N is the number of boundaries, g is the genus, n is always 1 here. So this will reduce to a factor that goes with e to the s naught, and then a power series in 1 over e to the 2s naught, right? Where this object here is just the same Schwarzschild partition function evaluated on hyperbolic surfaces of a fixed genus. Don't ask me how to compute this. There's just an iterative procedure that allows you to compute this once you know the lowest order term. And the important message here is that now this full partition function, including higher genus effects, can be reorganized as a power series expansion controlled by e to the minus 2s naught. Okay? Now we can look at a completely different setting, a completely different problem, dealing with statistical ensembles of Hermitian matrices, labeled that I'm calling here H, which are sampled according to some probability measure. So this defines a measure. The measure depends on some function of the matrix V that I call the matrix potential. And if you interpret this H as the Hamiltonian of some system, you can define a notion of an average partition function, which will just be an observable in this ensemble computed by integrating the trace of e to the minus beta h against the measure. Okay, now bear with me. This will connect to what we did before in the next slide. It is a fact in random matrix theory that if you take the size of the matrix to be large, you get a useful repackaging of this random matrix integral of this form. So you have a leading order term that goes with the size of the matrix, and then you get an expression like this, where this G, this label G appearing here, is the genus of the matrix diagrams that contribute to any given term of the sum. If you remember, first year of masters, if you did the TOEFL notation for Feynman diagrams in Yang-Mills theory, you had this double line notation, and if you try to fit each of those diagrams in a two-dimensional surface, that surface will have a particular genus for a particular diagram. That is the genus that we're talking about here. Anyway, there's a way to match the topology of the surfaces where these matrix diagrams can fit and two-dimensional surfaces that I drew before. Now I put the two expressions I had next to each other. And now I will just state a very useful fact that in both of these sides, right, you can systematically compute higher order terms in this genus expansion in terms of recursion relations that depend on the lowest order terms. And the two recursion relations are the same, both for JT gravity and for the random matrix integral. And the fancy technical name for those are, on the JT side, is something called the Mirzakhani's recursion relations for Weyl-Peterson volumes of two-dimensional surfaces. And in the random matrix side, it's, well, those two names for matrix integrals. You can also show that you can match the lowest order term of the X expansion by carefully choosing the matrix potential that defines the matrix ensemble. And if I put those two things together, I conclude that JT gravity, including higher topologies, is effectively described by a type of matrix integral. So that's how you include arbitrarily high topologies in JT gravity. Yeah, you can draw pictures about what that means for the Schwarzschild bilocal. Essentially, the corrections that you get are things that will essentially link those two sides that are divided by this bulk line that you drew. And the rough intuitive way of thinking about this is that these connections between the two sides, they are encoding the effect of coupling a matter theory, in this case, the two-dimensional CFT, or the theory whose expectation values you're computing. You're coupling that to a quantum chaotic system that is described by random matrix statistics, in this case, the black hole. But at the end of the day, all that amounts to is, when you had an observable, such as the Schwarzschild bilocal, that depended on products of densities of states, you will now replace that product of density of states with something that we call the pair density correlator, which is like a correlation function of eigenvalue distribution. It's the joint probability of this matrix ensemble having matrix H, which has an eigenvalue exactly at E equals E1 and E equals E2. Or rather, given that the matrix has an eigenvalue equal to E1, how likely is it that it will also have an eigenvalue equal to E2? So the Schwarzschild bilocal contained a product of densities of states. Now you replace that with this two-point function of energy eigenvalues of the random matrix theory, and the rest remains the same. Now, what will come to save the day is the fact that this pair density correlator is also known exactly, at least in the regime of small energy separations, which is the thing that will dominate in the large Z limit that we want to consider. And now you can just, again, plug this into the Schwarzschild bilocal, apply approximations, and compute the results in this limit. And the result looks like this. In orange, the curve is the semi-classical prediction. In blue is the result once you include the wormhole corrections. And this green is a plateau value that you get as Z goes to infinity. And the message here is then that the semi-classical expectation for the entropy of the thermal radiation in the exterior of the black hole will deviate from what you expect semi-classically. By translating the z coordinates into the proper length away from the horizon, you can compute this proper length as a function of the parameters of the problem. The important thing to know here is that this is doubly non-perturbative in G Newton, because both S0 and C secretly depend on 1 over G Newton. So this is a highly non-perturbative effect that you would have no hope of getting if you just did semi-classical gravity as a series expansion in G Newton. But in this example, we can do it in full. So yeah, this is the end. Now just to recap what we did. We studied a few examples of quantum gravitational effects on local observers in JT gravity. We motivated this notion of gravitationally dressed observers in this model, or we gave an explicit description of what the observer meant in terms of the gravitational degree of freedom. We motivated this choice of dressing by mapping bulk conformal isometries with the boundary time translation, which is motivated by this connection between conformal isometries and geometric modular flow. And we extended this dressing also to include 2 asymptotic boundaries in a way that allowed you to describe the black hole interior with similar tools. And then, by using that, we learned that an infalling or Dewey detector with a suitable gravitational dressing is sensitive to the Schwarzschild fluctuations. In particular, you can tell the location of the black hole horizon and its temperature just by using local measurements. And this is a true quantum gravity effect that in this model is definitely not visible semi-classically. And to include non-perturbative effects coming from a higher genus expansion, we studied the thermal entropy of the black hole atmosphere, and we also saw that we obtained corrections from the semi-classical results. In particular, the matrix model completion of JT gravity leads to a plateau in the entanglement entropy. So there's a cutoff for how big the entanglement entropy can be outside the black hole in this model. Just to name some things that you might want to consider thinking about. Given this protocol, it's very easy to just think of other kinds of thought experiments in RQI and JT gravity. One thing to name, gravitationally dressed entanglement harvesting. You have a 2-point function. You have detector trajectories. Just, do what we always like to do when we first start doing RQI. Another option, or another thing that is interesting to me, is further understanding this connection between the Schwarzschild dressing and geometric modular flow. Our result was that the map between the Schwarzschild and the bulk isometries was necessary to make this connection even be possible. But it's not clear at all that it is one-to-one, so this is something that I think would be interesting to understand. And finally, I think this framework gives a very useful tool to study things like quantum reference frames in a fully non-perturbative model of quantum gravity, which could be, a notion of, since you have a way to define bulk observers in the quantum regime, you might have a quantum reference frame for free there. So this is something that would be interesting to understand. So this is what I had to say. These are my collaborators, and thank you for listening.
Do we have questions? Just one quick one.
What about the page curve?
Well, the page curve is solved already, so.
No, but I mean, you get this asymptote to the entanglement entropy, right?
Yeah.
What is the reason that you don't say something that decreases like the page curve in this model?
Oh, because in this case, I don't have evaporation at all. It's a static solution. So I'm just looking at the thermal field double with radiation in a thermal equilibrium with the black hole.
That's fair.
Yeah.
Would you be able to incorporate something like this, you think? Like if you were to use these techniques of gluing the ADS solution?
Yeah. But I think this might already be done implicitly.
Okay.
So, yeah.
Thank you.
Okay. Do you have any more questions? Okay, then let's thank Bruno again. And well, before closing the session, I just wanted to thank everybody who has participated in the session and in the meeting in general. And well, I also wanted to briefly say, also in case anybody is watching, that the idea of this kind of a meeting, well, as has been to gather a bunch of people that we are all postdocs or very young professors or PhD students that are about to finish, so that we can, well, on one hand, spark collaborations and talk to each other, but also kind of create some sense of community, because in the end, we are the people that are going to be colleagues for the largest amount of time, I guess. So it's good that we know each other and we know what we work on. And the idea would be ideally to be able to do this perhaps yearly and be able to repeat it. So in that sense, it will be important also to get like feedback regarding what you have found interesting, what you think was not worth it. And well, also finally, just to close everything, I would like to thank the Cost Action for the support, because the funding that they provided was very important for a successful development of the meeting. And with that, I would like to thank again everybody who has participated both in the RQI Circuit session and in the meeting in general.